Close your eyes. Let your shoulders fall away from your ears. Let your hands rest open, palms upward, fingers loose. Let your breath come slowly, in through the nose, and out through the mouth, and in again, and out again. And with each breath, let the room around you grow a little quieter, a little more distant, a little more like the soft edge of a dream. You do not need to hold on to anything right now. You do not need to remember where you are, or what tomorrow requires of you, or how long it has been since you last slept well. All of that belongs to another version of tonight. This version is different. This version is quiet. Let us go somewhere together, you and I. Let us drift backward, slowly and without urgency, through the long corridor of human time, past the last century and the one before it, past centuries that had no names, past the first cities and the first kings, all the way back to a world that was green and wet and warm, a world that hummed with insect wings and the low murmur of standing water, a world in which something very small and very ancient had already begun its long, slow, patient relationship with the human body. If this voice helps you rest tonight, if it is a companion to the quiet hours, then consider subscribing to Plague Lullaby, but only if you are still awake to hear these words. And if you are still awake, do not worry. We have a very long way to go together, and the road is unhurried, and the darkness here is soft. We are going to spend the next several hours exploring the complete history of malaria, a disease so old, so vast, so quietly woven into the fabric of human civilization, that some historians believe it has claimed more human lives than any other cause in recorded history, perhaps in all of human history combined. This is not a story told in urgency. This is a story told in the slow, patient voice that malaria itself has always used. The voice of centuries, the voice of something that does not hurry because it does not need to. Let us begin. There is a genus of single-celled organisms called Plasmodium, and it is older than humanity itself by a very comfortable margin. Before the first human beings walked upright across the grasslands of Eastern Africa, Plasmodium was already there, already cycling through the blood of birds and reptiles, and the small, warm-bodied creatures that would eventually become primates, already perfecting its complicated and deeply intimate relationship with the mosquitoes of the genus Anopheles, already learning, over millions of years and countless generations, exactly how to move from one warm body to another, without being noticed until it was far too late to do anything about it. The evolutionary history of the Plasmodium parasite is, in a certain light, more impressive than almost anything human beings have ever accomplished, because it represents 4 billion years of accumulated intelligence, encoded not in thought but in chemistry, not in strategy but in biology, not in intention but in the patient, unthinking drift of natural selection across geological time. It is worth pausing in the soft quiet of this evening to sit with that thought for a moment. Plasmodium did not decide to infect human beings. It did not choose us. It simply found us, the way water finds the lowest point in a landscape, the way a root finds moisture in dry soil, following the gradient of warmth and blood and exhalation that all living creatures leave behind them as they move through the world. We were simply the next available vessel, and the parasite, with no mind and no awareness and no cruelty whatsoever, settled in. The earliest evidence of Plasmodium falciparum, which is the most deadly of the 5 species of malaria parasite that infect human beings today, has been traced through genetic analysis to a period somewhere between 50,000 and 100,000 years ago, which places its origins squarely within the long, slow dawn of anatomically modern human beings. Researchers working with ancient DNA have reconstructed portions of the parasite's evolutionary tree, and what they have found suggests that as human populations grew, as we moved out of Africa and into new climates and new landscapes, malaria moved with us, adapting, shifting, finding new species of Anopheles mosquito to serve as its carrier in each new environment, never quite losing its hold on the human body, no matter how far that body traveled or how much the world around it changed. A 2024 study published in the journal Nature, led by researcher Megan Michel of the Max Planck Harvard Research Center, analyzed genomic data from 36 ancient malaria-infected individuals, spanning approximately 5,500 years of human history across 5 continents, and what it revealed was a pattern of spread that followed, with almost haunting fidelity, the great movements of human civilization itself, the trade routes, and the migration paths, and the military campaigns, and the colonial expeditions, as if malaria were not merely a disease but a quiet record of everywhere humanity had ever chosen to go. It is worth noting, in these early moments of our story, that the 4 species of Plasmodium, most commonly discussed in the history of human malaria, are Plasmodium falciparum, Plasmodium vivax, Plasmodium malaria, and Plasmodium ovale, each with its own character, its own preferred geography, its own particular relationship with the human immune system. Of these, Plasmodium falciparum is by far the most dangerous, responsible for the majority of severe cases and fatalities, particularly in sub-Saharan Africa, and it is the one whose history is most deeply entangled with the great devastations that give this story its weight. Plasmodium vivax, by contrast, causes a less immediately lethal illness, but carries with it the particular quality of relapse, the ability to lie dormant in the liver for months or even years before re-emerging in the bloodstream, a quality that has made it extraordinarily difficult to fully eliminate from any population it has entered. The parasite's life cycle itself is one of the more elaborate performances in the biological world, involving 2 hosts, a mosquito and a mammal, and a series of transformations so complex that it took scientists working across 3 continents, across the better part of a century, to fully map it. We will return to those scientists and their careful, painstaking work in due course. For now, let us simply note that what enters the human body from a mosquito's bite is not a fully formed parasite, but something far smaller and more quietly devastating, a thread of living chemistry called a sporozoite, thinner than a hair, invisible to any eye, that travels through the bloodstream to the liver in a matter of minutes, and begins, without any drama whatsoever, the slow and methodical work of making more of itself. And so it was that long before anyone knew what malaria was, long before any human being had a name for the cold shivers and the burning fevers and the deep bone ache that came with the disease, long before any physician had thought to look at blood through a lens and see what was living there, human beings were already suffering from it, already dying from it, already building their lives and their cities and their civilizations in the shadow of it. The ancient Egyptians knew something that caused fevers in the low-lying delta regions of the Nile, somewhere in the warm, still water near the river's mouth, where the mosquitoes gathered in the evenings. Some of the mummified remains from ancient Egypt show enlarged spleens, which is a characteristic response of the human body to repeated malarial infection, as the spleen works to filter the parasite-damaged blood cells that accumulate during illness. In 2010, scientists analyzing the mummified remains of the pharaoh Tutankhamun, who ruled Egypt from approximately 1333 to 1323 BCE, recovered traces of Plasmodium falciparum DNA from the blood preserved within the mummy's tissues, suggesting that the young king, who died at approximately 19 years of age, may have been suffering from malaria at the time of his death, alongside other conditions that have been identified in his remains. It is a quiet and somewhat melancholy detail, this image of the boy king in his gilded chamber, attended by physicians who could not have known what was happening in his blood, who had no framework for understanding the invisible architecture of his dying. The ancient world had many names for the experience of malaria, though it had no name for the disease itself in any modern sense. In ancient Mesopotamia, texts inscribed on clay tablets describe a recurring fever deity, a spiritual personification of the shaking cold that preceded the burning heat, and the incantations and rituals used to address this force were among the earliest recorded medical interventions in human history, though they were understood by those who performed them not as medicine, but as prayer, not as chemistry, but as communication with the forces that governed illness. In ancient India, the Atharva Veda, one of the oldest Sanskrit texts, which scholars date to somewhere between 1500 and 1000 BCE, contains passages describing a fever called takman, which is characterized by chills and burning heat and rhythmic periodicity, symptoms that correspond closely to the pattern of malarial fever cycles, and which is associated with the rainy season and with marshland, an association that places it with remarkable precision near the very environments where Anopheles mosquitoes breed most densely. In ancient China, medical texts from the era of the Shang dynasty, dating back some 3,500 years, describe a disease called nue, characterized by periodic fevers, chills, and the enlargement of the spleen. And these texts recommend for its treatment a plant called qingkao, which is the Chinese name for Artemisia annua, a plant whose active compound, artemisinin, would not be identified by modern science until the 1970s, when a Chinese pharmacologist named Tu Yu would isolate it and in doing so, create what is now the most important antimalarial drug in the world. It is a thread that stretches from the Shang dynasty all the way to Tu Yu's Nobel Prize, awarded in 2015, a thread of botanical knowledge passed forward through 3,500 years of human civilization, and it is one of the quieter miracles of this entire story. Hippocrates, the Greek physician who lived from approximately 460 to 370 BCE, and who is often described as the father of Western medicine, wrote extensively about the periodic fevers of the Greek mainland and the islands, and he was among the first figures in the Western tradition to attempt a systematic, naturalistic explanation for disease rather than a supernatural one. In his writings, Hippocrates described what he called tertian fever, which recurred every third day by the counting method of his era, and quartan fever, which recurred every fourth day, distinctions that correspond reasonably well to the infection cycles of different Plasmodium species, with Plasmodium vivax and Plasmodium falciparum producing the shortest cycle, and Plasmodium malaria producing the longer one. Hippocrates observed, with great care, and without yet possessing any means of explaining what he saw, that these fevers were most common in people who lived near marshes and stagnant water, and that they were most prevalent in the late summer and early autumn, during the months when the temperatures were warmest and the mosquito populations were at their peak. Though, of course, Hippocrates did not know about mosquitoes in any relevant sense, and his explanation for the association between marshes and fever was that the bad air rising from the water was somehow responsible for the illness, an explanation that would persist in medical thought with remarkable tenacity for more than 2,000 years. The word malaria itself derives from the Italian words malaria, meaning bad air, and it was in use in Italy at least by the medieval period, though in various forms and with various spellings it appears in Italian texts much earlier. The Romans suffered enormously from malaria, and the disease is believed by many historians to have played a significant role in the decline of Roman civilization, not through any single catastrophic epidemic, but through the slow chronic attrition of a disease that weakened agricultural labor forces, depopulated the lowland farming regions of central Italy, sapped the energy and productivity of urban populations, and placed a persistent drain on the physical and economic resources of the empire over many centuries. The Pontine marshes, the vast wetlands that stretched south of Rome along the Tyrrhenian coast, were for centuries among the most malaria-ridden landscapes in Europe, and the Roman effort to drain and cultivate them, which was never fully successful until the Mussolini era in the 20th century, was in part a public health initiative, an attempt to put distance between the population of Rome and the damp, warm, insect-heavy environments that experience had long associated with the seasonal fevers. Julius Caesar is thought by some historians to have suffered from the disease, as is Augustus, and the poet Horace made reference to the fevers of the Roman Campania in his writing, with the matter-of-fact familiarity of someone who had seen them many times, the way one mentions the heat of summer or the cold of January as a feature of the world rather than a catastrophe. During the long centuries of the medieval period in Europe, malaria continued its quiet work across the lowlands of Italy, Spain, France, England, and the Low Countries, wherever the combination of warm summers and standing water provided the conditions that Anopheles mosquitoes required to breed in sufficient numbers to sustain transmission. Medieval physicians, working within a medical framework inherited from Galen and Hippocrates and refined across centuries of scholarship, understood the periodic fevers as an imbalance of the four humours, and they prescribed treatments accordingly, including phlebotomy and various herbal preparations, none of which address the underlying cause of the illness, but some of which may have provided mild symptomatic relief. The church played an important role in the social management of malaria during this period, as it did with most illness, and saints' days and pilgrimage routes were organized in ways that sometimes, inadvertently, moved large numbers of susceptible people through highly endemic regions during the worst transmission seasons, with predictable results. It is worth noting that the population of England during this period included a significant burden of malaria, particularly in the low-lying counties of Kent, Essex, and the Somerset levels, where the combination of tidal marshes and warm summers created conditions favourable to Anopheles atroparvus, the British mosquito species capable of transmitting the parasite, and records from the 16th and 17th centuries suggest that the ague, as the English called their periodic fevers, was considered almost a normal condition of life in those regions, an accepted feature of the landscape like the mud and the mist, something one endured rather than something one expected to escape. The relationship between malaria and the great civilizational project of agriculture is one of the most profound and least frequently discussed aspects of the disease's history, and it is worth pausing here, in the soft quiet of this telling, to consider it. For most of human prehistory, our ancestors lived in small, mobile groups, moving through the landscape in patterns that did not favor the dense mosquito populations required for efficient malaria transmission, and genetic studies suggest that the deadliest form of the parasite, Plasmodium falciparum, may have had limited access to human hosts. During this period, its transmission rates constrained by the simple fact that people were spread too thinly across the landscape to sustain the chains of infection that the disease requires. It was agriculture that changed this. It was the clearing of forests to plant crops, the creation of irrigation systems that left standing water across wide areas, the building of permanent settlements where people lived in close proximity and returned to the same places season after season. It was all of this that created the conditions in which malaria could thrive at a scale it had never achieved before. And the bitter irony of that history is that the very transformation that allowed human civilization to grow and feed itself and build cities and write poetry and sail ships also created the ecological conditions that delivered generations of human beings into the patient company of Plasmodium, and the disease grew as civilization grew, and the two became, over millennia, almost indistinguishable companions. It is a strange kind of intimacy, this relationship between a civilization and its plague. And as you rest here in the quiet of your room, breathing slowly and letting the weight of history pass gently through you, it is worth simply acknowledging that this intimacy is one of the oldest facts about the human species. Older than writing, older than kingdoms, older than the first city wall. And that the story we are telling tonight is not simply the story of a disease, but the story of the slow, patient, completely unhurried relationship between human life and the microscopic world that has always lived alongside it, within it, and in many ways ahead of it. Over the next several centuries of our narrative, we will follow this relationship through the ancient empires of the Mediterranean and the river valleys of Asia, and we will find malaria always there, always present, always doing its quiet, patient, ancient work. The ancient world did not lack for observation. What it lacked was the conceptual framework to make sense of what it was observing, and this gap between careful noticing and meaningful understanding is one of the great recurring themes of the history of malaria and of medicine more generally. Physicians in ancient Greece and Rome could describe the fevers with remarkable precision, noting their periodicity, their seasonal patterns, their association with particular landscapes, their tendency to recur in the same patient year after year. And yet all of this careful observation led, for more than 2,000 years, to explanations that were physically incorrect, rooted in the logic of humoral medicine and miasmatic theory, rather than in any accurate understanding of infection and biological causation. There is no reproach in saying this. The miasmatic theory, the idea that disease arose from corrupted air and decaying organic matter, was a rational inference from available evidence, a reasonable conclusion drawn from the observation that people who lived near marshes and rotting vegetation were more likely to fall ill. And it was not until the late 19th century that the germ theory of disease provided the conceptual tools necessary to explain why this correlation existed without attributing it to the air itself. In the meantime, the miasmatic theory shaped 2 millennia of public health practice, urban planning, and medical treatment. And some of that practice was, almost accidentally, quite effective, because draining marshes, moving towns to higher ground, and improving ventilation did reduce the mosquito populations and therefore did reduce malaria transmission, even if no one understood exactly why. The great pandemic histories of the ancient Mediterranean tend to focus on plague, on the epidemic diseases that arrived suddenly and killed quickly and dramatically enough to leave vivid written records. The plague of Athens in 430 BCE which may have been typhus or typhoid or something else entirely. The Antonine plague of the 2nd century CE, the plague of Cyprian in the 3rd century, the great Justinianic plague of the 6th century, that was almost certainly bubonic plague. Malaria does not appear in these histories in the same way, because malaria does not announce itself with the sudden, catastrophic drama of a pandemic. It works more quietly than that. It is a background hum rather than a sudden percussion, a slow diminishment rather than a sudden catastrophe. And its effects, though enormous in aggregate, are distributed across time in a way that makes them harder to perceive as a single event, and therefore easier to overlook in the historical record. A town that loses 1 in 20 of its children every year to malarial fever does not generate the same urgent, concentrated testimony as a town that loses half its population in 3 months to plague. Even if the cumulative toll of the former, over generations, exceeds the toll of the latter by a considerable margin. It is a feature of malaria's particular kind of devastation that it tends to become invisible through familiarity, absorbed into the normal texture of life, in the way that chronic sorrow, after long enough, can become almost indistinguishable from the ordinary sadness of being alive. In the Roman Empire, the interaction between military expansion and malaria transmission created patterns of disease burden that historians are still working to fully understand and document. The Roman legions, moving through the marshlands of central Italy, through the river valleys of Gaul and Germania, and the Iberian Peninsula, through the floodplains of Egypt and the Middle East, carried with them both the susceptible bodies of soldiers who had grown up in non-endemic regions, and the logistical infrastructure of roads, and camps that often, inadvertently, created new mosquito breeding sites along their routes. There is evidence in ancient sources, in the letters of commanders and the administrative records of provincial governors, that the periodic fevers were a significant cause of military attrition, reducing the effective strength of legions during campaign seasons, and contributing to the failure of operations that might otherwise have succeeded. The Emperor Augustus, who ruled from 27 BCE to 14 CE, was believed by ancient sources to have suffered from recurring fevers throughout his adult life, fevers that his physician Antonius Musa treated with cold water therapy, a treatment that may have provided some symptomatic relief without addressing the underlying cause in any meaningful way. Augustus spent considerable effort trying to drain and improve the malarial lowlands of central Italy, and his urban planning in Rome included attention to water management and drainage in ways that may have been partly motivated by the persistent association between standing water and disease. It was in the context of the late Roman Empire and the long transition into the early medieval period that malaria began to interact with the great demographic catastrophes of that era in ways that historians have been debating for a very long time. The question of what caused the decline of the Roman Empire is one of the most extensively argued questions in all of historical scholarship, and malaria figures in several serious hypotheses, not as the sole cause or the primary cause, but as a significant contributing factor, a chronic drain on the agricultural, productivity, and general health of the Italian and Mediterranean populations that made the empire progressively less resilient in the face of the other pressures it was experiencing. The political instability, the economic strain, the external pressures from migrating peoples on the northern and eastern frontiers. Edward Gibbon, in his monumental work, The History of the Decline and Fall of the Roman Empire, published in volumes between 1776 and 1789, gave relatively little direct attention to disease as a historical force, working within the intellectual framework of his era, which emphasized political and military causation. But later historians, and particularly historians of medicine, writing in the 20th century, have increasingly emphasized the role of endemic disease in shaping the long-term capacity of ancient societies to sustain themselves. William McNeill's 1976 work Plagues and Peoples was among the most influential articulations of this perspective, arguing that epidemic and endemic disease has been one of the primary determinants of historical change, operating largely below the level of conscious political decision-making in the bodies of ordinary people living ordinary lives in ordinary places. The early medieval period in Europe, the centuries between approximately 500 and 1000 CE, saw malaria continue its steady presence in the lowlands of the continent. And it is worth noting that this period also saw the beginning of the slow, gradual demographic recovery of European populations after the devastations of the late antique epidemics, a recovery that proceeded unevenly across the continent and was repeatedly interrupted by new outbreaks of various diseases. In the monasteries of early medieval Europe, monks who served as physicians and herbalists compiled texts describing the treatments available for the periodic fevers, and many of these texts drew on classical sources, on Galen and Dioscorides and Hippocrates, preserving and transmitting the accumulated medical knowledge of the ancient world through the difficult centuries of the early medieval period. Willow bark, which contains salicylates related to aspirin, was sometimes used to reduce fever, and various aromatic plants were burned near the sick, in a practice that had obvious connections to the miasmatic theory, but which may, in some cases, have had modest insect repellent properties as a secondary effect. The great monasteries often sat in low-lying, damp locations that their founders had chosen partly for their remoteness and solitude, and partly because such land was cheap and easily available, and the monks who lived in these places suffered considerably from the ague and the tertian fever, a fact that appears often enough in the chronicles and correspondence of the period to suggest that it was simply accepted as part of the rhythm of monastic life, a seasonal trial to be endured with prayer and patience, and the remedies that the infirmary could provide. The Islamic Golden Age, which spanned roughly from the 8th to the 13th century CE, produced some of the most sophisticated medical scholarship of the medieval world, and it engaged seriously and systematically with the problem of the periodic fevers. Avicenna, the Persian physician and philosopher whose full name was Ibn Sina, and who lived from 980 to 1037 CE, wrote extensively about the malarial fevers in his monumental medical encyclopedia, The Canon of Medicine, a work so comprehensive and so authoritative that it remained a standard text in both Islamic and European medical schools for several centuries after his death. Avicenna distinguished carefully between the different types of periodic fever, describing their onset, their duration, their characteristic patterns of chill and heat and sweating, and he noted the association with marshland and season, with the same careful attention that Hippocrates had brought to the subject 15 centuries earlier. His explanations remained within the framework of humoral theory, as was appropriate for a physician working within the intellectual traditions of his era, but his clinical descriptions were precise enough to be recognizable to any modern physician who reads them, and they demonstrate that the experience of malaria, whatever its cause was believed to be, was consistent enough across centuries and cultures to generate very similar clinical descriptions. whenever a careful observer sat down to record what they saw. The spread of Islam across North Africa, the Middle East, Persia, and into Central Asia, and the Indian subcontinent during the 7th and 8th centuries created new trade networks and new patterns of human movement, and these patterns inevitably shaped the geography of malaria transmission in ways that historians are still mapping. The Great Silk Road trading networks, which connected China to the Mediterranean across the length of Central Asia, passed through many malarial zones, and the merchants and pilgrims and soldiers and diplomats who traveled these routes carried malaria parasites with them in their blood, potentially introducing new strains into populations that had limited immunity to them. The Hajj, the annual pilgrimage to Mecca, that became one of the most significant recurring mass movements of people in the medieval world, brought together hundreds of thousands of individuals from vastly different disease environments, creating conditions in which infectious diseases of many kinds could be transmitted between populations that had no previous exposure to each other's pathogens. It is a pattern that will recur many times in our story, this intersection of faith and commerce and human longing for connection with the invisible biological reality that connects all living bodies to one another in ways that no faith or commerce ever anticipated. The Crusades, which brought armies from Northern and Western Europe into the malaria endemic landscapes of the Eastern Mediterranean and the Levant, beginning in 109 6 CE, provide one of the more extensively documented intersections of malaria and medieval military history. The crusading armies, composed largely of men from regions of northern Europe, where malaria transmission was either absent or relatively mild, arrived in the summer and autumn months in the Jordan Valley, the coastal plains of Lebanon and Palestine, and the delta regions of Egypt with little or no acquired immunity to the strains of plasmodium circulating in those regions, and they suffered accordingly. The fevers that struck these armies are described in many of the chronicles of the Crusades, often attributed to the heat and the strange air of the Holy Land, described as a punishment for sin or a trial of faith, or simply as the expected hardship of warfare in a foreign country. But their timing and their pattern and their association with specific landscapes are consistent with malaria, and historians of medicines who have reviewed the primary sources generally regard malaria as one of the significant medical factors in the military outcomes of several crusading campaigns. The Fourth Crusade of 1202 to 1204, which famously never reached the Holy Land at all, and instead sacked Constantinople, was shaped by many factors, but the health of the armies and the accumulated losses of previous campaigns to disease were among them. The Black Death, which swept across Eurasia, beginning in 1347, and killed somewhere between a third and half of the population of Europe within a few years, was an event so catastrophic and so sudden that it fundamentally altered the demographic, economic, social, and cultural landscape of the continent in ways that took centuries to fully resolve. In the context of malaria's history, the Black Death is significant not because malaria caused it, or was particularly associated with it, but because the demographic collapse it produced created new conditions for malaria transmission in the lowland regions of Europe. Depopulated farmland reverted to marshland in some areas, as the human labor required to maintain drainage systems and cultivated fields was suddenly absent, and this ecological reversion may have temporarily increased mosquito breeding habitat in some regions. In other areas, the death of experienced agricultural workers meant that the land was managed differently, with different consequences for water management and drainage. The long-term effects of the Black Death on malaria transmission in Europe are complex and not fully understood, and historians continue to work through the available evidence, from parish records, estate accounts, and medical chronicles to reconstruct the picture. Over the next several centuries, as Europe slowly recovered from the demographic catastrophe of the 14th century and began the long economic and cultural expansion that would eventually produce the Renaissance and the Age of Exploration, malaria continued its patient presence in the marshlands and river valleys of the continent, shaping the health of populations in ways that were deeply felt even when they were not fully understood. The landscape of Italy, particularly the Roman Campagna and the coastal marshes of Tuscany and Sardinia, remained heavily malaria endemic throughout this period, and the recurring fevers of the autumn season were as much a feature of Italian life as the olive harvest or the grape vintage, something that artists and poets and letter writers mentioned in passing as a background condition of existence, without any expectation that it might one day be explained or eliminated. Meanwhile, in other parts of the world, in the great river valleys of sub-Saharan Africa, in the monsoon-washed plains of southern Asia, in the warm lowlands of Southeast Asia and the tropical Americas, the same disease was doing the same patient, ancient work in landscapes and bodies that history has far less frequently recorded, but that suffered no less for the absence of documentation. The New World lay on the far side of the Atlantic Ocean, a distance that had kept it largely separate from the disease ecologies of the Old World for as long as human beings had been living on both sides. And when European ships began crossing that ocean in the last decade of the 15th century, they did not cross it alone. They brought with them, in the bodies of the sailors and soldiers and settlers who made those crossings, a biological cargo of infectious agents for which the indigenous populations of the Americas had no immunological preparation, and the consequences of this biological collision were, as historians now understand quite well, among the most devastating demographic events in recorded human history. Malaria's role in this story is complicated because some forms of malaria may have existed in the Americas before European contact, carried by early human migrants crossing the Bering Land Bridge tens of thousands of years earlier, though the genetic evidence on this point remains contested among researchers. The 2024 study by Megan Michel and colleagues found evidence suggesting that Plasmodium vivax was present in South America in the pre-Columbian period, though they also found evidence of a genetically distinct European origin strain being introduced to Peru in the early colonial period, within the first century after contact. What is less contested is that Plasmodium falciparum, the most deadly species of malaria parasite, was introduced to the Americas by European colonizers and by the enslaved African people they brought with them, and that its arrival in the tropical lowlands of the Caribbean, Central America, and South America added one more catastrophic element to the already devastating epidemiological transformation that was destroying indigenous American populations in the decades after 1492. Christopher Columbus made his first landfall in the Caribbean in October of 1492 on an island in the Bahamas that he named San Salvador. And within a very few years of that arrival, the indigenous Taino people of Hispaniola, who had greeted the first Europeans with gifts and cautious hospitality, were dying in enormous numbers from the diseases that the Europeans had brought with them. The early colonial period in the Caribbean was characterized by a kind of epidemiological chaos that no one at the time had any framework to comprehend or manage, as populations with no prior exposure to smallpox, measles, influenza, and various other infectious diseases encountered all of them in rapid succession, each wave of illness arriving before the previous one had fully resolved. Each wave finding a population already weakened by the last. Malaria was one strand in this catastrophe, and while it is difficult to disentangle its contribution from the contributions of the other diseases that were simultaneously devastating Caribbean populations, it is clear that the warm, wet, heavily forested lowlands of the Caribbean islands provided excellent conditions for Anopheles mosquitoes, and that once Plasmodium was introduced into these environments, it established itself with considerable efficiency. The Spaniards who came to the Caribbean seeking gold and glory found themselves instead in a landscape where fever was a constant companion, where men who had survived the crossing from Seville or Cadiz were laid low within weeks of their arrival by the shaking cold and burning heat of the tertian fever, and where the mortality among the European settlers and soldiers, particularly in the first years before some partial acquired immunity could develop, was staggering enough to require constant replacement of the labour force and the garrison. It was in the context of this colonial disease environment that the history of the most important antimalarial treatment in Western medicine before the 20th century begins, and that history takes place in the high Andes of South America, in the territories of what is now Peru and Ecuador, where the indigenous Quechua people had long known of the fever-reducing properties of the bark of a particular tree. The tree in question was a species of cinchona, a genus of flowering plants native to the cloud forests of the Andean foothills, and its bark contained a compound that would eventually be isolated and named quinine, which would become the standard Western treatment for malaria from the 17th century until well into the 20th. The story of how this knowledge passed from the indigenous populations of the Andes to the pharmacopoeias of Europe is, like most stories of this kind, more complicated than the simplified version that appears in many general histories. The most commonly repeated account credits the Countess of Chinchon, the wife of a Spanish viceroy of Peru, with introducing the bark to Spain after it cured her of a fever in 1638, and Linnaeus later named the genus Cinchona in her honor. Though modern historians examining the diary of the Count of Chinchon have found no mention of his wife being cured of fever by the bark, suggesting that this part of the story may be apocryphal. What is more certain is that by the 1630s and 1640s, Jesuit missionaries working in Peru had become aware of the bark's properties and were using it both to treat their own fevers and to distribute it to indigenous populations, and it was through the Jesuit network that the treatment first came to the attention of European physicians, acquiring in the process the name Jesuit's bark or Jesuit's powder. The introduction of Jesuit's bark into European medicine was not without controversy, as the treatment's association with the Catholic Jesuit order made it politically fraught. In the context of the religious conflicts of 17th century Europe, and Protestant physicians in particular, were sometimes reluctant to recommend a treatment that seemed to carry Catholic associations. Robert Talbot, an English apothecary of the 17th century, who had no formal medical training, but who had spent time in the marshy regions of Essex developing what he described as a secret remedy for the ague, became one of the most famous healers of his era by administering preparations that were, unknown to his patients, based largely on cinchona bark mixed with wine, and he guarded the formula of his remedy with considerable commercial shrewdness, declining to reveal it publicly during his lifetime. and selling it eventually to King Louis XIV of France in 1679 for a considerable sum. The king published the formula after Talbor's death in 1681, and the revelation that this celebrated secret remedy was essentially cinchona bark in a essentially somewhat disguised form contributed to the gradual acceptance of the bark as a legitimate treatment within mainstream European medicine. It was not until 1820 that French chemists Pierre-Joseph Pelletier and Joseph Bien-Aimé Caventou isolated and purified quinine from cinchona bark, giving physicians for the first time a defined compound in a measurable dose, rather than a preparation of variable potency from dried and powdered plant material. This moment of purification, this act of extracting one substance from the complex chemistry of a plant that had been used for nearly 2 centuries in its whole and unrefined form, represents one of the foundational moments of modern pharmacology, and it gave malaria treatment a precision and a consistency that it had previously lacked. The transatlantic slave trade, which transported an estimated 12 million African people to the Americas between the 16th and 19th centuries, is one of the most terrible chapters in human history, and its relationship to malaria is both medically significant and deeply morally complex. The people who were enslaved and transported from West and Central Africa to work in the plantations of the Caribbean and the American South came, in many cases, from regions of the world where Plasmodium falciparum was highly endemic, and where, over generations of exposure, portions of the population had developed partial genetic protections against the most severe forms of the disease. The most important of these protections is the sickle cell trait, a genetic variant in the hemoglobin gene that, when inherited in one copy from one parent, provides significant protection against severe falciparum malaria while producing only mild health consequences in the carrier. This genetic variant is far more common in populations with long historical exposure to falciparum malaria, which is why it is prevalent in sub-Saharan Africa, and its presence in enslaved populations meant that those populations were, on average, more resistant to the malaria that was endemic in the lowland plantations of the American South and the Caribbean than the European colonizers, and their children were. This biological reality was observed, misinterpreted, and weaponized by the defenders of slavery, who used the relative resistance of enslaved African people to malaria as a justification for the institution, arguing that African people were biologically suited to labor in tropical and subtropical environments in ways that European people were not, an argument that was both scientifically confused and morally obscene. But that was deployed with considerable frequency in the political debates over slavery in the 18th and 19th centuries. The plantation economy of the American South developed in close and complicated relationship with malaria, and the geography of the disease shaped the economic geography of the region in ways that are still legible in the historical record. The coastal lowlands of South Carolina and Georgia, with their extensive rice paddies and tidal marshes, were among the most heavily malaria-endemic regions in North America. And the cultivation of rice in these environments, which required the maintenance of flooded fields that created ideal mosquito breeding habitat, was both economically dependent upon and a significant driver of malaria transmission in the region. The mortality among white settlers in the South Carolina Low Country in the 17th and 18th centuries was high enough that it contributed to the demand for enslaved labor, because the death rate among European indentured servants was so severe that the plantation system could not sustain itself without a labor force that had somewhat greater biological resistance to the endemic diseases of the region. Historians such as Peter McCandless and Margaret Humphreys have examined these relationships carefully, and their work demonstrates the degree to which the social and economic structures of the antebellum South were shaped, at a fundamental level, by the biological realities of malaria transmission in a malarial landscape. In the tropical and subtropical regions of Africa and Asia, the history of malaria during the same period is a history of endemic disease so deeply embedded in daily life that it shaped everything from the timing of agricultural work to the location of settlements to the patterns of trade and migration. The great West African kingdoms of this era, the Mali Empire, the Songhai Empire, the kingdoms of the Sahel and the forest zones, existed in landscapes where malaria was intensely endemic and their populations had developed over generations. The partial immunological tolerance that comes from repeated childhood exposure to the parasite, an immunity that is never complete and never permanent, but that does reduce the severity of disease in adults who survived repeated infections in childhood. This immunity was one of the factors that shaped the military dynamics of the era, because European armies is tempting to operate in West African coastal environments, suffered devastating mortality from malaria that their African adversaries were somewhat better equipped to survive. And this biological asymmetry was one of the reasons why European colonial penetration of the African interior was delayed until the second half of the 19th century, when quinine began to be used as a prophylactic, as a preventive treatment taken regularly to suppress malaria transmission, rather than merely as a treatment administered after illness had already established itself. The colonial project in India unfolded in a landscape where malaria had been endemic for millennia in the river valleys and floodplains of the Ganges and the Brahmaputra, in the Terai belt along the southern edge of the Himalayas, in the coastal deltas of the subcontinent's eastern and western coasts, and in the hot, low-lying plains of the Deccan. The British East India Company, which extended its commercial and eventually its military and administrative presence across India from the early 17th century onward, encountered malaria at every stage of its expansion, and the disease was among the most significant causes of mortality among European soldiers and administrators stationed in the subcontinent. The hill stations, those charming settlements at altitude that the British established in the foothills of the Himalayas and in the Western Ghats, were developed partly for reasons of social preference, and partly because higher altitudes meant lower malaria transmission and the pattern of seasonal migration to the hills during the hot weather, when malaria transmission was most intense in the lowlands, became one of the defining features of colonial life in India. Meanwhile, the vast majority of the Indian population, who had no access to hill stations and who could not avoid working in the malarial lowlands throughout the transmission season, bore an enormous burden of disease that was not only a humanitarian catastrophe in its own right, but also a significant drag on agricultural productivity and economic activity throughout the subcontinent. It is worth pausing here, at the quiet midpoint of this long span of centuries, to note the strange symmetry of malaria's relationship with the great colonial enterprises of the early modern period. Malaria was, in some ways, a barrier to European expansion, killing European soldiers and settlers in the tropical regions they sought to control and slowing the pace of colonization in Africa and parts of Asia. And yet malaria was also, in another sense, a consequence and an engine of colonization, spread to new regions by the very ships and armies that were simultaneously being killed by it, moved across oceans in the blood of enslaved people and colonizers alike, introduced to the Americas in the traumatic biological exchanges of the contact period, and then sustained and amplified by the agricultural systems that colonialism created, the rice paddies and the sugar plantations and the cotton fields that flooded the land and drove mosquito populations to new heights. There is no neat moral lesson in this symmetry, no satisfying narrative of justice or irony, only the quiet, continuing observation that malaria, like all diseases, does not have sides in human conflicts, does not distinguish between the powerful and the powerless, between the colonizer and the colonized, between those who cause suffering and those who bear it. It finds all bodies equally available, and the distinctions that matter to human beings in their political and moral lives are irrelevant to the biology of a parasite that has been doing this work with complete indifference to human categories for 50,000 years. The 19th century was the century in which humanity finally began to develop the scientific tools necessary to understand what malaria actually was. And the story of that understanding is a story of patient observation, careful experimentation, and the slow, sometimes contested, sometimes bitterly argued accumulation of evidence in the face of theories that had been accepted for so long that they felt less like hypotheses than like common sense. The miasmatic theory of disease, which held that illness arose from bad air and corrupted organic vapors, had been the dominant explanatory framework for the periodic fevers for more than 2,000 years, and it was not overthrown quickly or easily or without resistance, even as the evidence against it accumulated with increasing force throughout the middle decades of the century. The story of how the germ theory of disease gradually replaced miasmatic theory in the second half of the 19th century is one of the central narratives of modern medicine. And malaria occupies a particular and important place within that story, because the agent responsible for malaria proved to be neither a bacterium nor a virus, but a eukaryotic parasite, a creature of considerable biological complexity, whose discovery required both the development of new microscopic techniques and the willingness to look for a cause of disease that no one had previously imagined finding. Alphonse Laveran was a French military physician who was serving with the French army in Algeria when, on the 6th of November, 1880, he examined a blood sample taken from a patient suffering from malaria and saw, under his microscope, something that no one had ever described before. He saw, in the blood of his patient, transparent, moving organisms attached to the surface of red blood cells, creatures that were clearly alive, clearly biological, and clearly not any artifact of the microscopy or the preparation of the sample. Laveran recognized that what he was seeing was almost certainly the cause of malaria, the living agent of the disease that had previously been attributed to bad air, and he published his findings in a paper that appeared in December of 1880, arguing that the malaria parasite was a protozoan, a single-celled eukaryotic organism, and that it lived within the red blood cells of its human hosts during part of its life cycle. The reception of Laveran's discovery was initially skeptical, as was common for discoveries that challenged established frameworks, and it took several years and the confirmatory work of other researchers, including the Italian microscopists Camillo Golgi, Ettore Marchiafava, and Angelo Celli, who were working with improved microscopes and better staining techniques in Rome during the 1880s, before the identification of the malaria parasite became widely accepted within the medical community. Laveran was awarded the Nobel Prize in Physiology or Medicine in 1907 for this discovery, one of the earlier Nobel Prizes given for work in tropical medicine. And his name remains associated with the parasite to this day in the genus name Plasmodium, though the naming of the genus was actually established by other researchers building on his foundational observation. Meanwhile, in the years following Laveran's discovery, the question of how the parasite passed from one human being to another remained open and actively contested. Laveran himself had suggested that mosquitoes might be involved, and other researchers had made similar suggestions, but the evidence remained circumstantial, and the mechanisms by which a protozoan parasite might complete part of its life cycle in an insect rather than a vertebrate host were far from understood. It was Ronald Ross, a British physician born in Almora, in what was then British India, who worked out the role of mosquitoes in malaria transmission. And he did it through a combination of careful experimental work, extraordinary persistence, and what he himself described as an almost obsessive determination to solve a problem that had frustrated him and everyone before him for years. Ross had become interested in the malaria problem in the late 1880s, partly through his encounters with Laveran's work, and partly through conversations with Patrick Manson, the Scottish physician who had already demonstrated that filariasis was transmitted by mosquitoes, and who believed that mosquitoes were likely involved in malaria transmission as well. Working in India with limited equipment and under considerable administrative pressure to attend to other duties, Ross spent years dissecting mosquitoes and examining their tissues for evidence of Plasmodium. And on the 20th of August, 1897, in the city of Secunderabad, he found what he had been looking for: oocysts containing developing malaria parasites in the stomach wall of a particular species of Anopheles mosquito that had been fed on the blood of a malaria patient. The following year, working with avian malaria in birds, because he had been transferred to a region of India where human malaria was less available for study, he completed the full life cycle of the parasite, demonstrating that it developed in the mosquito's body, migrated to the salivary glands, and was injected into a new host when the mosquito fed. Ross was awarded the Nobel Prize in Physiology or Medicine in 1902 for this work, and the 20th of August is still observed as World Mosquito Day, in recognition of the anniversary of his crucial discovery. The Italian school of malariologists working in Rome and in the malarial lowlands of Sardinia and Calabria during the 1890s made equally important contributions to the understanding of the disease during this period, and it is worth noting that their work proceeded largely in parallel with Ross's, following different methods and focusing on different aspects of the problem. Giovanni Battista Grassi, Amico Bignami, and Giuseppe Bastianelli worked together to demonstrate in 1898 that Plasmodium falciparum was transmitted specifically by Anopheles mosquitoes rather than by other mosquito genera, and Grassi in particular spent considerable effort identifying the specific species of Anopheles present in Italy and demonstrating the correlation between their distribution and the distribution of malaria in the Italian countryside. There was a priority dispute between Ross and Grassi over credit for the discovery of mosquito transmission that became acrimonious and persisted for years, reflecting the competitive pressures of scientific achievement and the national pride that was invested in the work on both sides. But from the perspective of the history of medicine, the important point is simply that by the end of 1898, The mechanism of malaria transmission had been conclusively demonstrated, and the disease that had puzzled physicians for more than 2,000 years was at last understood well enough that rational control measures could be designed and implemented. The practical implications of knowing that malaria was transmitted by Anopheles mosquitoes rather than by bad air were substantial, though the translation of laboratory knowledge into effective public health interventions took many years and required the development of new tools and organizational structures that did not yet exist. One of the first demonstrations of the potential for mosquito control to reduce malaria transmission was carried out in Cuba and Panama in the early years of the 20th century in the context of the American military occupation of Cuba after the Spanish-American War of 1898 and the subsequent construction of the Panama Canal, which began in earnest under American direction in 1904. The French had begun work on the Panama Canal in 1881 under the direction of Ferdinand de Lesseps, the engineer who had successfully completed the Suez Canal. But the project had collapsed in 1889 after the deaths of an estimated 22,000 workers from yellow fever and malaria, and the accompanying financial scandals. And when the Americans resumed the project, they did so in the knowledge that controlling the disease environment was a precondition for completing the engineering work. William Crawford Gorgas, who had served as the chief sanitary officer in Havana during the yellow fever eradication campaign there, and who understood the practical application of vector control, was appointed sanitary officer for the Panama Canal zone. And over the years between 1904 and 1913, he supervised a comprehensive program of mosquito control that included drainage of standing water, oiling of water surfaces to kill mosquito larvae, screening of buildings, use of quinine as a prophylactic, and the clearing of vegetation near inhabited areas. The results were dramatic. Malaria mortality among canal workers fell from enormously high levels in the early years of the project to very much lower levels by 1910, and the canal was completed in 1914, a demonstration that understanding the biology of a disease and applying that understanding systematically could transform a public health situation that had previously seemed intractable. The early decades of the 20th century also saw the development of a scientific understanding of the full life cycle of the malaria parasite, including the stages that occur within the liver, the organ that had been overlooked in earlier accounts of the disease's biology. It had been recognized from early in the era of parasitological research that the malaria parasite spent time in the red blood cells, where it multiplied, destroyed the cells, released new parasites into the bloodstream, and in doing so, produced the characteristic cycles of fever, chills, and sweating that had been described in clinical accounts for millennia. But the question of what the parasite did in the period between its injection into the body by a mosquito and its first appearance in the blood cells, a period that could last anywhere from a week to 2 weeks, depending on the species, remained unclear until the work of Henry Short and Cyril Garnham in the 1940s and 1950s demonstrated that the sporozoites injected by the mosquito traveled to the liver, where they underwent a phase of multiplication known as the exoerythrocytic cycle before releasing merozoites into the bloodstream to begin the blood stage infection. For Plasmodium vivax and Plasmodium ovale, Short and Garnham's work also eventually revealed the existence of dormant liver stage parasites called hypnozoites, which could persist in the liver for months or years without causing active disease, and then reactivate to produce new blood stage infections. an explanation for the pattern of relapsing malaria that clinicians had observed and been unable to explain for a very long time. The story of quinine's use as a prophylactic in colonial contexts during the 19th and early 20th centuries is one of the clearest examples of how medical knowledge, when it is available, can alter the balance between disease and human activity in a particular landscape. The British colonial administration in India, which dealt with enormous malaria mortality among both its military and civilian populations, began promoting the regular use of quinine as a preventive measure from the mid-19th century onward. And the gin and tonic, which was originally developed as a palatable way to consume the bitter quinine-containing tonic water that was issued to British soldiers and administrators in India, is one of the more whimsical cultural artifacts of this history, a social tradition born from the practical problem of getting people to take their medicine regularly in a context where the medicine tasted disagreeable enough that they were inclined to avoid it. The addition of gin to the tonic water, along with lime to prevent scurvy, and sugar to cut the bitterness, produced a preparation that people were considerably more willing to consume on a daily basis. And while the quinine content of modern tonic water is far too low to provide any antimalarial protection, the drink itself carries forward a faint chemical memory of the 19th century colonial encounter with malaria prophylaxis. It is one of those small, strange connections between everyday habits and the deep history of human disease that rewards a moment's quiet consideration here in the soft darkness of a late evening, as the world outside grows still and the past drifts slowly closer. The role of malaria in the history of warfare during the 19th and early 20th centuries is extensive and well documented, and it serves as a reminder that the disease's influence on human events was not confined to the domestic and agricultural spheres, but extended into the military and geopolitical. During the American Civil War, which was fought between 1861 and 1865, malaria was among the most significant causes of illness and disability in both the Union and Confederate armies, particularly in the campaigns conducted in the lowland South, in the river valleys of Virginia and the Carolinas and the Mississippi Basin, where transmission was intense during the warm months. The Union Army's medical records, which were preserved and analyzed in detail in the years after the war, showed that malaria accounted for a very large proportion of the total sick days experienced by Union soldiers, and that it significantly reduced the effective fighting strength of units stationed in endemic areas during the transmission season. Quinine was issued to Union soldiers as both a treatment and a prophylactic, and the logistical challenge of supplying adequate quantities of it to the field armies was a significant military problem, one that the Union Army's medical department worked to address throughout the war with varying degrees of success. In the Confederate Army, quinine was far more difficult to obtain because the Union naval blockade restricted the importation of the drug, and Southern physicians were forced to experiment with substitute preparations derived from indigenous plants with limited effectiveness. As the 19th century drew toward its close, the combination of Laveran's identification of the parasite, Ross's demonstration of mosquito transmission, and the accumulated clinical experience of generations of physicians working in malarial regions had created the foundation for a genuine scientific understanding of malaria that had been entirely absent from human knowledge for the previous 50,000 years of the disease's history. This foundation was not yet a solution, and the enormous challenge of translating biological understanding into practical, sustained, large-scale disease control in the face of poverty, political instability, inadequate infrastructure, and the sheer geographical vastness of the malarial world was a challenge that the 20th century would take up with enormous energy and only partial success. But the transition from the ancient era of miasma and mystery to the modern era of parasitology and vector biology was now complete, and the disease that had been known for millennia as the bad air was now understood to be something very different, something far more specific, and in principle far more addressable. A living organism with a complex life cycle, a mosquito vector with identifiable habits and breeding requirements, and therefore a target that human intelligence and human organization. The 20th century opened with a disease that was finally understood, and a world that was not yet equipped to act decisively on that understanding. And this gap between knowledge and capacity is one of the defining tensions of malaria's modern history, a tension that would take the better part of 100 years to even partially resolve, and that in many respects remains unresolved today. Ronald Ross, returning to England from India, and later working in West Africa, spent much of his later career advocating for the systematic application of mosquito control measures as a public health strategy, and he developed mathematical models of malaria transmission that were among the earliest attempts to apply quantitative reasoning to an epidemiological problem, models that describe the relationship between mosquito density and transmission rates, and predicted the level of vector control required to reduce transmission below the threshold at which the disease could sustain itself in a population. These models, which Ross published in various forms between 1905 and 1911, were far ahead of their time in their conceptual ambition, and the tradition of mathematical epidemiology that Ross founded has grown, over the century since, into one of the most important tools available to public health planners, applied not only to malaria, but to the full range of infectious diseases that challenge modern medicine. The practical application of his insights was slow, however, constrained by the organizational and financial limitations of the colonial public health systems that were responsible for malaria control in most of the world's endemic regions. Systems that were understaffed, underfunded, and often more focused on protecting European administrators and soldiers than on addressing the disease burden of the indigenous populations who suffered from it most. It is worth noting, with the gentle clarity of historical distance, that the period between Ross's discovery in 1897 and the development of truly effective large-scale malaria control in the 1940s and 1950s was a period in which millions of people died from a disease whose mechanism was fully understood, a fact that carries its own quiet weight in the history of public health and of the priorities that shaped it. The organizational problem of malaria control, the question of how to mobilize the resources and the political will to implement vector control and treatment programs across the enormous geographical areas where the disease was endemic, proved in many ways harder to solve than the scientific problem of understanding what malaria was. And it required not only medical knowledge, but political transformation, economic development, and the building of public health institutions capable of sustained action at the scale that the disease required. The first decades of the 20th century saw a series of malaria control initiatives in different parts of the world that demonstrated both the possibilities and the limitations of the tools then available. And these initiatives ranged from the highly successful to the tragically incomplete, depending largely on the resources committed to them and the political context in which they operated. In Italy, the physician Angelo Celli, who had been one of the important figures in the Italian school of malariological research, devoted the later part of his career to a comprehensive program of malaria control in the Italian countryside that combined quinine distribution, agricultural improvement, better housing for rural workers, and public health education, an approach that recognized the social and economic determinants of malaria transmission rather than treating it purely as a technical problem, amenable to a purely technical solution. Celli worked in partnership with his wife, Anna Fraenzel Celli, who was herself a physician and a significant contributor to the social medicine work of the program, and their joint effort in the Roman Campagna in the years before and after the turn of the century is one of the earlier examples in the historical record of a malaria control program that explicitly addressed the conditions of poverty and inadequate housing that made rural workers so vulnerable to the disease. The results in their study areas were encouraging, with significant reductions in malaria morbidity and mortality in the communities where the program was most fully implemented, but the resources available were insufficient to extend the program across the full extent of the endemic zone in Italy, and the disease remained widespread in the Italian countryside through the first decades of the century. During the same period, the American authorities administering the Panama Canal Zone were demonstrating, with the more substantial resources available to them, that systematic mosquito control could dramatically reduce malaria transmission in a defined geographic area, a demonstration that was widely noted in the international public health community, and that influenced the design of subsequent control programs in other regions. The tension between what was scientifically possible, what was financially feasible, and what was politically prioritized is a thread that runs through the entire 20th century history of malaria control. And it is a thread that, if followed to its end, leads not to any triumphant resolution, but to a continuing negotiation between human aspiration and human limitation. The period of the First World War, from 1914 to 1918, brought malaria into dramatic contact with the military operations of multiple nations in multiple theaters, and the experience of that war both demonstrated the disease's capacity to devastate military forces and provided a powerful stimulus for the development of new antimalarial drugs that would become crucial in the following decades. The Salonika campaign, fought by Allied forces in the malaria endemic lowlands of what is now northern Greece, beginning in 1915, became one of the most notorious examples of military malaria in the entire history of warfare, with an estimated 80 Syrzos Allied soldiers hospitalized for malaria during the course of the campaign, a figure that significantly exceeded the number hospitalized for wounds in some periods of the operation. The German and Austro-Hungarian forces facing them fared somewhat better in the malaria statistics, partly because of somewhat more favorable positions, and partly because of differences in quinine supply and distribution, but malaria was a significant burden on all sides in that theatre. And the phrase attributed to a German general, that malaria was his best ally in that campaign, whether accurately attributed or not, captures something true about the role the disease played in determining the pace and the outcomes of military operations in the region. In Mesopotamia, where British and imperial forces were fighting Ottoman troops in the river valleys of what is now Iraq, malaria was similarly pervasive. and the medical challenges of maintaining an effective fighting force in an intensely endemic environment were among the most serious operational problems that the campaign's commanders faced. The experience of the war stimulated significant research investment in synthetic antimalarial drugs, driven by the recognition that dependence on natural quinine from South American cinchona plantations was a strategic vulnerability, and German pharmaceutical chemists, in particular, building on the country's strong tradition of synthetic or organic chemistry, began systematic programs to develop compounds that could replicate or improve upon quinine's antimalarial properties without requiring a natural plant source. This research program would eventually, through a process that extended well into the interwar period and the Second World War, produce the compounds that transform malaria treatment in the mid-20th century. And it is a reminder that even the most devastating conflicts in human history sometimes generate, as an inadvertent byproduct, scientific advances that serve the longer-term interests of human health. The interwar years, the 2 decades between the armistice of 1918 and the outbreak of the Second World War in 1939, saw significant advances in both the science of malaria and the organizational development of international public health, and these 2 tracks of development ran alongside each other in ways that were sometimes collaborative and sometimes frustratingly parallel. The League of Nations Health Organization, the predecessor of the World Health Organization, established a malaria commission in 1923 that brought together researchers and public health officials from multiple countries to share knowledge and coordinate approaches to malaria control. And it was through the work of this commission that some of the foundational concepts of modern malaria epidemiology were developed and disseminated. The Rockefeller Foundation, drawing on the substantial philanthropic resources of the American oil fortune that had created it, funded malaria control programs in multiple countries during this period, including a major campaign in Sardinia that began in the 1920s, and that combined drainage, quinine distribution, and larviciding of mosquito breeding sites with public health education for rural communities. German pharmaceutical research produced pamaquine in 1926 and mepacrine, also known as quinacrine or atabrine, in 1930, compounds that offered antimalarial activity against different stages of the parasite's life cycle, though both had significant side effects that limited their acceptability and their therapeutic usefulness. The Brazilian malariologist Oswaldo Cruz had, earlier in the century, demonstrated the possibility of eliminating a mosquito species from a large geographic area, working against Aedes aegypti in the context of yellow fever control, and this demonstration of the feasibility of vector elimination, rather than merely vector reduction, influenced the thinking of malariologists who were beginning to consider whether the eradication of malaria mosquitoes, rather than simply their control, might one day be a realistic goal. The world was not yet ready for eradication thinking, but the seed of that ambition was present in the scientific community of the interwar years, waiting for the technological development that would make it seem, for a brief and hopeful period, genuinely achievable. The Second World War, fought between 1939 and 1945 across a range of theatres that included some of the most intensely malaria-endemic regions on Earth, produced another enormous surge of military malaria and another powerful stimulus to antimalarial drug development, and the outcomes of this drug research would reshape the treatment of the disease for the better part of the next half-century. In the Pacific Theatre, where American, British, Australian, and Japanese forces fought across the islands and jungles of a region where Plasmodium falciparum and Plasmodium vivax were both highly prevalent. Malaria was in many campaigns a greater cause of military incapacity than enemy action, and commanders on all sides struggled to maintain effective fighting forces in the face of disease rates that sometimes hospitalized a majority of a unit's strength within weeks of its deployment to a new area. General Douglas MacArthur, commanding Allied forces in the Southwest Pacific, was reported to have said at one point that his army was dying on its feet from malaria, and the urgency of the military situation drove the United States and its allies to invest enormous resources in the search for effective antimalarial treatments that could keep soldiers operational in the field. The Japanese occupation of the Dutch East Indies in 1942, which cut off the Allied supply of natural quinine from the cinchona plantations of Java, made the development of synthetic alternatives an immediate strategic necessity rather than a long-term research goal, and the American government organized a large-scale cooperative research program involving academic chemists, pharmaceutical companies, and military medical researchers that eventually tested more than 14,000 compounds for antimalarial activity. Chloroquine, a synthetic compound that had been developed by German chemists in the 1930s, but initially set aside because it was considered too toxic for clinical use, was rediscovered and retested during this program, and found to be both safe and highly effective. And it became, after the war, the dominant antimalarial treatment of the mid-20th century, used by hundreds of millions of people across the world for the better part of 4 decades. The wartime experience also demonstrated the critical importance of drug compliance, because soldiers who took their antimalarial medications regularly were dramatically healthier than those who did not, and the practical challenge of ensuring that soldiers, and later civilians, took their medications on the required schedule was one that public health authorities would grapple with throughout the subsequent decades of malaria control. The creation of the World Health Organization in 1948 as one of the specialized agencies of the newly established United Nations system brought a new organizational framework to the international effort against malaria and other infectious diseases, and it brought with it the ambition and the institutional structure to think about disease control at a truly global scale for the first time. The WO's early years coincided with the emergence of a new technological tool that seemed, to many public health authorities at the time, to represent a fundamental breakthrough in the possibility of disease control. And that tool was dichlorodiphenyltrichloroethane, the insecticide known universally as DDT. DDT had been developed during the Second World War, partly for use in controlling malaria and typhus among military populations, and its effectiveness against mosquitoes and other insect vectors was remarkable by the standards of anything previously available, allowing the residual spraying of interior walls of houses to kill resting mosquitoes for weeks or months after a single application, with a degree of efficiency and persistence that no previous insecticide had matched. In India, a pilot program of DDT, spraying in the years immediately after the war, produced dramatic reductions in malaria transmission in the areas treated, and similar results were seen in other parts of the world. And these early successes generated an atmosphere of considerable optimisms about the possibility of using DDT-based residual spraying to achieve not merely control, but the complete eradication of malaria from large parts of the world. It was this optimism, combined with the availability of chloroquine as an effective treatment, the post-war institutional infrastructure of the WHO, and the political will that accompanied the founding of the United Nations system, that led, in 1955, to the launch of the Global Malaria Eradication Program, one of the most ambitious public health initiatives in human history, a program that proposed to eliminate malaria from the entire world within a defined timeframe through the systematic application of DDT spraying and chloroquine treatment across all endemic regions. The Global Malaria Eradication Program, launched by the World Health Organization in 1955, was an expression of a particular moment in the history of human confidence. A moment when the combination of new technologies, new institutions, and the post-war spirit of international cooperation seemed to make impossible things appear merely difficult, and difficult things appear merely a matter of resources and organization. The program was led by Fred Soper, an American public health official who had spent decades working on vector control programs in Latin America, and who brought to the malaria eradication effort a conviction that systematic, well-organized spraying campaigns, if pursued with sufficient rigor and consistency, could interrupt malaria transmission in any region of the world. The strategy was straightforward in its conception. Spray the interior walls of houses with DDT, which would kill the Anopheles mosquitoes that rested on those walls after taking a blood meal, thus preventing them from surviving long enough to complete the transmission cycle. Simultaneously provide chloroquine treatment to any cases that continued to occur, thus eliminating the human reservoir of the parasite, and sustain both interventions long enough that the parasite, denied its vector and its host reservoir, would simply disappear from the treated area in regions with favorable ecological conditions, where mosquito species depended heavily on indoor resting, and where access to populations was relatively straightforward. The strategy worked with impressive effectiveness. Greece, which had been one of the most heavily malaria-endemic countries in Europe, with hundreds of thousands of cases per year, in the early post-war period, achieved malaria elimination by 1974 through a combination of DDT spraying and improved economic conditions. Italy, whose malaria burdens had persisted for millennia through the long history of the Roman Campagna and the Pontine marshes, and the endemic zones of Sardinia and Sicily, achieved elimination by 1970 through a similar combination of insecticide spraying, drainage improvements, and socioeconomic development that improved housing quality and reduced human-mosquito contact. The United States, where malaria had been endemic in the South and in parts of the West through much of American history, achieved elimination in 1951, before the global program formally began, through a combination of residual DDT spraying by the National Malaria Eradication Program, improved housing, and the post-war economic development that transformed the American South. In Sri Lanka, then Ceylon, the results of DDT spraying were particularly dramatic, reducing the annual malaria case count from an estimated 2 million cases in the late 1940s to just 17 cases reported in 1963, a reduction so spectacular that it seemed to confirm the most optimistic projections of the eradication program's architects. And yet, and this word carries the weight of all the subsequent decades, the Global Malaria Eradication Program ultimately fell short of its most ambitious goal, and the story of why it fell short is one of the more important and instructive stories in the history of public health, a story about the gap between what is technically possible in optimal conditions and what is achievable in the real complexity of the world as it actually exists. The program explicitly excluded sub-Saharan Africa from its initial eradication goals, a decision that reflected both the practical difficulty of implementing systematic spraying campaigns in the ecological and infrastructural conditions of tropical Africa and a set of political and institutional priorities that, in retrospect, reflected the unequal valuation of human life that characterized so much of the international system of that era. And this exclusion meant that the region with by far the highest malaria burden in the world was not part of the eradication effort at the moment of its greatest ambition. In the regions that were included in the program, the implementation encountered numerous difficulties, including the discovery that Anopheles gambiae, the principal malaria vector in much of tropical Africa, and various other Anopheles species in different parts of the world, were capable of developing behavioral resistance to DDT by changing their resting habits, moving from sprayed indoor surfaces to unsprayed outdoor environments, thus avoiding exposure to the insecticide without any genetic change, and rendering the residual spraying strategy ineffective. Genetic resistance to DDT also emerged in mosquito populations in some regions, as the intense selection pressure created by widespread insecticide use favored the survival and reproduction of individuals carrying genes that conferred resistance, and the spread of resistance alleles through mosquito populations occurred faster, in some areas, than the program had anticipated. The logistical challenges of maintaining consistent coverage in remote and difficult to access areas proved in many cases to be insurmountable with the resources available, and gaps in coverage allowed the parasite to persist in pockets from which it could invade previously cleared areas, particularly when spraying operations were interrupted by funding shortfalls or political difficulties. The combination of these factors, ecological complexity, insecticide resistance, logistical limitation, and the exclusion of the highest burden region, meant that by the late 1960s, the eradication program was struggling in many parts of the world, and in 1969, at the World Health Assembly in Boston, the WHO officially acknowledged that global eradication was not achievable in the foreseeable future with the available tools, and the program was effectively ended. The consequences of the eradication program's end were, in some regions, deeply tragic, and the story of Sri Lanka in the years after the spraying was halted illustrates, with particular clarity, the fragility of the gains that had been achieved. When DDT spraying was reduced in Sri Lanka in the early 1960s, following the dramatic success of the program in reducing cases to near zero levels, the malaria resurged with devastating speed, rising from those 17 cases in 1963 to over 1 million cases by 1969, a resurgence that reflected both the suspension of the vector control measures and the fact that the program's success had, paradoxically, contributed to its own undoing, because the near elimination of malaria had reduced population immunity and created a large cohort of susceptible individuals who were severely affected when the disease returned. A similar pattern of resurgence, following the reduction or cessation of control measures, was observed in India, in parts of Central America, and in other regions where the program had achieved significant reductions in transmission, and these resurgences demonstrated with painful clarity that the elimination of malaria from an area does not eliminate the risk of its return, and that the maintenance of low transmission levels requires sustained commitment to control measures rather than a one-time achievement that can then be safely abandoned. The resurgences of the late 1960s and 1970s also coincided with the emergence of another threat that would progressively transform the treatment landscape of malaria over the following decades: the development of chloroquine resistance in Plasmodium falciparum. Chloroquine resistance was first documented in Southeast Asia and South America in the late 1950s and early 1960s, and it spread over the subsequent decades across virtually all of the malaria endemic regions of the world, eventually reaching sub-Saharan Africa in the 1970s and establishing itself across the continent during the 1980s. The emergence and spread of chloroquine resistance was a pharmaceutical catastrophe that removed from the arsenal of malaria treatment the safest, most affordable, and most widely used drug that had ever been deployed against the disease, and it left endemic populations, particularly in sub-Saharan Africa, increasingly dependent on alternative drugs that were more expensive, less available, and in some cases associated with more significant side effects. The discovery of artemisinin, which became the foundation of the most effective malaria treatment of the modern era, is a story that begins in China during the Cultural Revolution, in circumstances of considerable political constraint and scientific isolation, and it is one of the more remarkable episodes in the entire history of antimalarial drug development. In 1967, the Chinese government launched a secret military research project known as Project 523, initiated at the personal direction of Premier Zhou Enlai in response to a request from the North Vietnamese government for assistance with the malaria problem that was devastating North Vietnamese soldiers during the Vietnam War. Project 523 assembled a team of Chinese scientists to work on the development of new malaria treatments. And one of those scientists was Tu Youyou, a pharmacologist at the Academy of Traditional Chinese Medicine in Beijing, who had been trained in both Western pharmacology and traditional Chinese medicine. Tuyu's approach to the project drew on her knowledge of traditional Chinese medical texts, and she identified the plant, Artemisia annua, known in Chinese as Qinghao, as a promising candidate based on a reference in a 4th century text by the physician Gehong, who had described a preparation of the plant in cold water as a treatment for intermittent fever. The critical insight was that the active compound in Artemisia annua was heat sensitive and was being destroyed by the standard extraction process that had been used in earlier tests of the plant, and Tuyu's modification of the extraction method to use a lower temperature process, guided by the ancient text's description of cold water preparation, led to the isolation of a compound of much greater antimalarial activity. Artemisinin was first isolated in its pure form in 1972, and the Chinese research team demonstrated its high effectiveness against malaria parasites, including strains resistant to chloroquine, in both laboratory and clinical settings. The results of this research were not shared with the international scientific community until the late 1970s and early 1980s, when China began to open its research institutions to international collaboration, and the Western scientific world's awareness of artemisinin developed slowly through the 1980s, as the compound's remarkable properties became more widely known. You received the Nobel Prize in Physiology or Medicine in 2015, shared with the parasitologist William Campbell and the microbiologist Satoshi Omura for other work in antiparasitic drug development, and her prize was notable for being the first awarded to a Chinese scientist for work done in China, a recognition that came 43 years after the isolation of the compound. And that drew international attention to a discovery that had been proceeding in scientific isolation for most of the intervening period. The global AIDS epidemic, which emerged in the early 1980s and claimed the attention and the resources of international public health through the following decades, had complex and sometimes difficult interactions with malaria that are not always recognized in general histories of either disease. At the most direct biological level, HIV infections suppresses the immune system in ways that significantly increase the severity of malaria infections in co-infected individuals, and studies conducted in sub-Saharan Africa during the 1980s and 1990s demonstrated that HIV-positive adults experienced malaria attacks of greater severity and with higher parasite densities than HIV-negative adults living in the same areas, and that the interaction increased the risk of severe and fatal malaria, particularly in pregnant women in whom the combination of HIV and malaria placed both the mother and the developing pregnancy at very high risk. At the resource and attention level, the emergence of the AIDS epidemic drew both funding and scientific talent away from malaria research and control programs during a period when malaria's burden in sub-Saharan Africa was actually increasing, driven by chloroquine resistance, population growth, and the failure to maintain the control infrastructure that had existed in some countries during the eradication era. This diversion of resources was not a conspiracy or a deliberate choice to ignore malaria, but rather a consequence of the natural tendency of public health systems and research communities to focus their energy on the most visible and most novel emergency of the moment. And malaria, which had been endemic for millennia, lacked the acute crisis framing that commanded emergency attention in the way that AIDS did in the early years of the epidemic. The result was that, through much of the 1980s and into the 1990s, malaria mortality in sub-Saharan Africa was rising, driven by drug resistance and inadequate control measures, while the international attention and funding that might have addressed this was concentrated elsewhere. And the children who were dying from malaria in those years were dying from a disease that was treatable, from drug resistance that was in principle preventable, in a silence that was one of the quieter catastrophes of the late 20th century. The 1990s brought a gradual reawakening of international attention to malaria, driven in part by the rising mortality data from sub-Saharan Africa, in part by the increasing recognition of artemisinin promise as a treatment, and in part by a broader shift in the global health agenda toward a recognition that infectious diseases of the poor represented both a humanitarian emergency and a development challenge that required sustained international investment. The World Health Organization's Rollback Malaria Initiative, launched in 1998 through a partnership between the WHO, UNICEF, the United Nations Development Programme, and the World Bank, was an attempt to reframe malaria control as an international priority and to mobilize coordinated action across the organizations and governments involved in the response. The initiative set ambitious targets for reducing malaria mortality and morbidity by 2010, targets that reflected genuine optimism about what could be achieved with the tools available. Insecticide-treated bed nets, artemisinin-based combination therapies, and indoor residual spraying. If those tools could be made available at scale to the populations who needed them, insecticide-treated bed nets, which create a physical and chemical barrier between sleeping humans and the night-biting Anopheles mosquitoes, responsible for most malaria transmission, had been demonstrated in clinical trials in multiple African countries during the 1980s and 1990s to reduce child malaria mortality by approximately 20% in settings of high transmission, a finding of enormous public health significance, and the long-lasting insecticidal nets that were developed in the late 1990s and early 2000s, which retained their insecticidal properties for 3 to 5 years without requiring retreatment, made the large-scale distribution of this tool more practically feasible than it had previously been. Artemisinin-based combination therapies, which paired artemisinin derivatives with partner drugs of different mechanisms of action in order to achieve high efficacy while protecting against the development of resistance to either component, were being developed and tested during the late 1990s and were, by the early 2000s, increasingly recognized as the treatment of choice for uncomplicated falciparum malaria, though the challenge of making these treatments available at the prices that poor countries and poor households could afford remained a significant obstacle to their widespread use. The founding of the Global Fund to fight AIDS, tuberculosis, and malaria in 2002 represented a significant escalation in the international financial commitment to malaria control, providing a new funding mechanism that was designed to channel substantial resources to endemic countries for the procurement and distribution of prevention and treatment tools. The Global Fund, which was structured as a public-private partnership with contributions from governments, the private sector, and foundations, provided grants to countries on the basis of national plans submitted through a competitive review process, and it rapidly became one of the largest single sources of malaria control financing in the world. The United States President's Malaria Initiative, launched in 2005 under President George W. Bush, with a commitment of $1.2 billion over 5 years, added another major bilateral funding stream for malaria control in sub-Saharan Africa, and a combination of these funding mechanisms with the distribution infrastructure of national malaria programs, UN agencies, and non-governmental organizations created, for the first time in the history of malaria control, a supply chain capable of moving insecticide-treated nets and artemisinin-based therapies to remote rural areas at something approaching the scale required to make a meaningful population-level impact. The results were measurable, and they represent one of the more encouraging episodes in the story of malaria and of global health more generally. Between 2000 and 2015, the global malaria mortality rate fell by approximately 47%, and among children under 5 years old in sub-Saharan Africa, the group most severely affected by the disease, the reduction was even more substantial. An estimated 6 million deaths were averted over this period by the scale-up of malaria prevention and treatment, a figure that represents an enormous reduction in human suffering and loss, even as it reminds us, by its very scale, of how much suffering and loss had been occurring in the decades before the interventions were scaled up. It is a fact worth sitting with quietly, this figure of 6 million lives preserved. In the same way that the earlier figures of millions of lives lost deserve their own quiet acknowledgement, because the history of malaria is a history in which both catastrophe and compassion have played their parts, and neither the suffering nor the progress should be allowed to disappear into the soft blur of statistical aggregation. The story of malaria in the first 2 decades of the 21st century is in many ways a story of genuine, measurable progress, interrupted by continuing challenges, a narrative of real achievements, won at great effort and held with great difficulty against the persistent biological intelligence of the parasite and its vector. The scale-up of insecticide-treated bed nets across sub-Saharan Africa achieved levels of population coverage that would have been almost unimaginable a decade earlier, with tens of millions of nets distributed through mass campaigns and routine antenatal care channels, and studies in multiple countries demonstrated that the expansion of net coverage was one of the primary drivers of the observed reductions in child malaria mortality. Indoor residual spraying programs, revitalized with newer classes of insecticides that could replace DDT in areas where resistance had developed, protected millions of households in high-burden countries. And the combination of nets and spraying in the same households was shown in some settings to provide greater protection than either intervention alone. Artemisinin-based combination therapies became the standard of care for uncomplicated malaria across the endemic world, and their availability in public health facilities and, increasingly, in the private retail sector transformed the case management of malaria in many countries, reducing the time between illness onset and effective treatment, and thereby reducing the proportion of cases that progressed to severe and potentially fatal disease. Seasonal malaria chemoprevention, the practice of giving prophylactic antimalarial drugs to young children in the Sahel region of West Africa during the months of highest transmission, was shown to reduce malaria incidence by approximately 75% in the treated population, and was scaled up across multiple countries as evidence accumulated and logistics were refined. Intermittent preventive treatment in pregnancy, which involves giving pregnant women antimalarial drugs at scheduled antenatal care visits, regardless of whether they are symptomatic, was demonstrated to reduce placental malaria and its associated risks of low birth weight and maternal anemia, and it was adopted as policy in multiple high-burden countries and supported by both national programs and international partners. The emergence of artemisinin resistance in the malaria parasite, first documented in the Mekong region of Southeast Asia in 2008 and confirmed in multiple studies over the following years, cast a shadow over the therapeutic progress of the previous decade and raised the serious possibility that malaria might become, in some parts of the world, effectively untreatable with the best available drugs. Artemisinin partial resistance, which manifests as a slowing of parasite clearance in response to artemisinin treatment, rather than as complete treatment failure, was associated with mutations in a gene called KELCH13, and the genetic epidemiology of the resistance showed that it had arisen independently on multiple occasions in the Mekong region, suggesting a strong selective pressure favoring resistant parasites in that area. More concerning still, mutations in KELCH13 associated with artemisinin partial resistance began to be detected in parasites from sub-Saharan Africa, a finding that, if confirmed to be spreading, would represent a threat to the malaria control gains of the previous 2 decades that was genuinely alarming to the global health community. The response of the WHO and national programs in the Mekong region included the withdrawal of oral artemisinin monotherapy and its replacement with artemisinin combination therapies, the intensification of surveillance for resistance markers, and the development of containment strategies designed to prevent the spread of resistant parasites beyond their current geographic range. Though the history of chloroquine resistance spreading from Southeast Asia and South America to Africa within a few decades provided an uncomfortably relevant precedent for what could happen if containment failed. The science of resistance was actively developing, with researchers working to understand the molecular mechanisms of resistance to identify new drug candidates that might serve as replacement partners or replacement treatments when the current generation of artemisinin combinations was threatened, and to develop the diagnostic tools that would allow surveillance systems to track the spread of resistance markers in real time. It was a race that the scientific community was aware it was running, and it was a race without a certain outcome, a reminder that biological evolution, operating without planning or intention, or any awareness of what it was doing, had always been one of the most formidable adversaries in the long human struggle with infectious disease. The development of the first malaria vaccine, approved for widespread use, RTSS, known by its commercial name Mosquirix, represented a milestone in the history of malaria that had been pursued for decades, and its approval by the European Medicines Agency in 2015, and the WHO's subsequent recommendation for pilot implementation in selected African countries in 2019 marked the culmination of 30 years of research and development by GlaxoSmithKline. In partnership with the Path Malaria Vaccine Initiative and with support from the Bill and Melinda Gates Foundation, the vaccine targets the circumsporozoite protein on the surface of the malaria sporozoite, the infective stage of the parasite injected by the mosquito, and it works by stimulating the immune system to produce antibodies that block the sporozoite's ability to infect liver cells. The clinical trial data showed that RTSS reduced clinical malaria episodes by approximately 39% and severe malaria episodes by approximately 31% in children aged 5 to 17 months over the trial period. A level of protection that, while modest by the standards of vaccines against other diseases, was regarded as significant in the context of a disease with such high transmission, intensity, and modeling studies suggested that even this partial protection, delivered at scale, could avert a substantial number of deaths each year in high-burden settings. The pilot implementation of RTSS in Ghana, Kenya, and Malawi beginning in 2019 reached more than 800,000 children in the first years of the program, and early data from the pilot suggested real-world effectiveness, consistent with the trial data, with reductions in severe malaria and malaria hospitalizations in the vaccinated cohorts. The R21 vaccine, developed at the University of Oxford's Jenner Institute in partnership with the Serum Institute of India, reported higher efficacy in trials conducted in Burkina Faso, and its approval and recommended use by the WHO in 2023 provided a second vaccine option with potentially greater supply capacity given the enormous production scale of the Serum Institute. These developments, seen together and in the context of the long history we have been tracing through this quiet evening, represent the beginning of a new era in the relationship between humanity and the oldest disease that has traveled alongside us. An era in which vaccination, added to the existing tools of bed nets, indoor spraying, combination therapies, and preventive treatment, offers a more comprehensive approach to reducing the burden of a disease that has resisted, for 50,000 years, every effort to dislodge it. And so we find ourselves at the midpoint of this long and gentle story, in a world that is simultaneously closer than it has ever been to controlling malaria, and still very far from having done so, in a world where the tools exist, but the resources and the systems to deploy them remain unequal to the scale of the problem, in a world where the progress of the last 2 decades coexists with the continuing reality that, as of the most recent WHO World Malaria Report, approximately 249 million cases of malaria occurred globally in 2022, and approximately 608,000 people died from the disease. The vast majority of them children under 5 years old in sub-Saharan Africa, dying from a disease that is in principle preventable with a net costing a few dollars and treatable with a drug course costing less than $1, dying from a gap between what is known and what is done that is not a gap of science, but a gap of will and resource and priority. It is not a comfortable place to rest within the story, but it is an honest one, and the quiet acknowledgement of it, here in the soft space between wakefulness and sleep, is its own small act of witnessing, its own small form of respect for the lives the disease has taken, and the lives it continues to take, patiently, as it has always done, in the warm and standing water, in the dark, in the long minutes before dawn. The geography of malaria in the 21st century is not the same geography that prevailed in the ancient world, or even in the colonial era, and the changes in that geography tell a story about both the progress that has been made and the deep structural inequalities that continue to shape which human bodies bear the heaviest burden of the disease. At the beginning of the 20th century, malaria was endemic on every inhabited continent, present in North America and Europe and Australia, and across the full sweep of Asia, Latin America, and Africa, touching the lives of populations that lived in temperate as well as tropical climates, and that spanned the full range of human economic conditions. By the early 21st century, malaria had been eliminated from all of Europe, from North America, from Australia, from the temperate regions of Asia, and from large parts of Latin America, and the disease had retreated into a narrowing band of the tropical world, with sub-Saharan Africa bearing approximately 94% of the global case burden and an even higher proportion of the global mortality. This contraction of the malaria map is, on one level, a story of genuine progress, of the accumulated effect of decades of control effort, economic development, improved housing, and the particular successes of elimination campaigns in specific countries and regions. On another level, it is a story of the deep and persistent connection between malaria and poverty, because the regions from which malaria has been eliminated are, without exception, regions that underwent significant economic development and built the infrastructure, screened housing, piped water, functioning health systems, educational systems, and road networks. That makes sustained malaria control possible, and the regions where malaria persists are, again, without exception, regions where poverty has constrained the development of that infrastructure. The correlation between malaria endemicity and poverty is so strong and so consistent that epidemiologists and economists have debated for decades which is the cause and which is the effect, with some researchers arguing that malaria causes poverty by reducing agricultural productivity, cognitive development in children, and adult labor capacity, and others arguing that poverty causes malaria by making it impossible to maintain the control measures that would reduce transmission. And the most honest answer, supported by the weight of the evidence, is probably that both are true, that malaria and poverty are bound together in a mutually reinforcing relationship that is difficult to break from either end without simultaneously addressing the other. Jeffrey Sachs and John Luke Gallup published an influential analysis in 2001, demonstrating that malaria endemic countries had per capita GDP growth rates approximately 1.3 percentage points lower per year than non-endemic countries over the preceding several decades, and that this economic penalty, compounded over time, represented an enormous cumulative disadvantage in the wealth of nations, a quantification of what had long been qualitatively understood about the relationship between the disease and the economic prospects of the societies it inhabited. The malaria endemic world is not poor because it is lazy or because it lacks resources or because it has made bad choices, but in significant part because it has been carrying for millennia a biological burden that the now wealthy world shed through a combination of ecological change, economic development, and deliberate disease control. A shedding that is available to the malaria endemic world as well, and that is proceeding unevenly and with difficulty as the control gains of the early 21st century accumulate. It is worth sitting with this understanding here in the quiet of a late evening, because it transforms the story of malaria from a natural tragedy into something more complex, something that involves human choices and human systems, as well as biological inevitability, and that therefore carries within it the possibility of different outcomes than the ones the past has produced. The landscape of the malarial world is changing, slowly and with setbacks, and the direction of that change, over the long arc of history, has been consistently toward a smaller domain for the disease, a domain that the combined efforts of science and public health and economic development are gradually but persistently contracting. And yet the pace of that contraction, measured against the continuing toll of 600,000 deaths per year, is a pace that many in the global health community regard as inadequate, and the question of how to accelerate it is one of the central questions of contemporary global health policy. The environmental dimensions of malaria, including the relationship between climate, land use, water management, and mosquito population dynamics, have always been central to the disease's history, and they have become increasingly prominent in discussions of malaria's future as the evidence for significant global climate change has accumulated. The connection between climate and malaria is, in its basic form, quite straightforward because Anopheles mosquitoes require temperatures above approximately 16 degrees Celsius for the malaria parasite to complete its development within the mosquito's body, and warmer temperatures accelerate both the mosquito's reproductive cycle and the parasite's development time within the mosquito, meaning that warmer climates support higher mosquito densities and faster transmission cycles. Rainfall is equally important because the standing water in which Anopheles mosquitoes breed requires precipitation, and the seasonal timing of rainfall patterns determines the seasonality of malaria transmission in many endemic regions. The implication of these relationships for a warming climate is that the geographic range of malaria transmissions could expand into highland areas and higher latitudes that are currently too cool to support transmission. That transmission seasons could lengthen in currently endemic areas, and that the intensity of transmission within existing endemic zones could increase. Although the actual prediction of climate change's effects on malaria is considerably more complex than these simple relationships suggest, because the relationship between temperature and mosquito survival is not linear, because human adaptive responses to climate change will also occur, and because the economic and public health systems that determine whether malaria transmission translates into malaria disease are themselves dynamic and changing. Studies of highland areas in East Africa, where populations living above the historical altitude limit for malaria transmission have little or no acquired immunity and could be severely affected by new malaria exposure, have identified evidence of upward shifts in the altitude distribution of malaria transmission in recent decades, consistent with the predicted effects of rising temperatures. Though the contribution of climate change relative to other factors such as changes in land use and health system capacity, is difficult to disentangle with precision. The Amazon basin, where deforestation and agricultural expansion create new mosquito breeding habitat and bring human populations into contact with malarial environments, represents another example of the interaction between environmental change and malaria risk. And studies in Brazil have documented increases in malaria incidence in areas of active frontier settlement and deforestation that demonstrate the continuing relevance of the ancient connection between land clearance and disease burden. In the African Sahel, where the malaria transmission season is determined primarily by rainfall, the predicted changes in precipitation patterns under various climate change scenarios carry significant implications for the timing, duration, and intensity of transmission seasons. And the seasonal malaria chemoprevention programs that have been scaled up in this region were designed around current transmission patterns that may need to be revisited as those patterns shift. The interaction between climate change and malaria is not a future concern, but a present one, already visible in epidemiological data from multiple regions. And it adds an additional dimension of urgency and complexity to the challenge of malaria control in the coming decades, requiring that public health systems not only address the current burden of the disease, but also anticipate and adapt to transmission patterns that are actively evolving. It is yet another reminder that the story of malaria is inseparable from the story of the human relationship with the natural world, that the disease is not a fixed and external force acting upon a passive humanity, but a dynamic participant in the ongoing interaction between human civilization and the ecological systems in which it is embedded, an interaction that is now being reshaped at an unprecedented rate by the accumulated consequences of 2 centuries of industrial activity, the experience of malaria elimination, the achievement of 0 locally transmitted cases in a previously endemic country, has accelerated notably in the 21st century, with a growing number of countries in Asia, Latin America, and the Middle East achieving this milestone and making formal application to the WHO for malaria-free certification. The WHO certification process requires that a country demonstrate the absence of indigenous malaria transmission for at least 3 consecutive years, the existence of a surveillance system capable of detecting any case that does occur, and the capacity to respond rapidly to prevent re-establishment of transmission if an imported case arrives. Sri Lanka, whose dramatic malaria resurgence after the premature scaling back of control in the 1960s, we noted earlier in this history, achieved malaria-free certification from the WHO in 2016, a particularly meaningful recognition given the country's tortured history with the disease and the decades of effort required to reach and sustain elimination after the lessons of the resurgence had been absorbed. China, which had reported 30 million malaria cases per year in the 1940s, and had been working on malaria elimination for decades through its national Malaria Elimination Program launched in 2010, achieved WHO certification as malaria-free in 2021, a remarkable achievement for a country of its size and epidemiological complexity, and one that represented the conclusion of an effort rooted in the same traditional medical knowledge from which artemisinin had emerged. El Salvador became the first Central American country to receive WAO malaria-free certification in 2021, and Algeria and Argentina received the same certification in 2019 and 2019 respectively, reflecting the progress of elimination efforts in their respective regions. These certifications represent genuine, hard-won achievements, and they are worth acknowledging with the quiet satisfaction that accompanies the resolution of a very old problem, even as we recognize that the problem is not resolved for the world as a whole, that the countries achieving elimination are, in most cases, countries whose malaria burdens were already relatively modest compared to the hyperendemic regions of sub-Saharan Africa, and that the technical and organizational challenges of achieving elimination in a country like Nigeria or the Democratic Republic of Congo, with their much higher transmission intensities and much more complex operational environments, are of a fundamentally different order of magnitude. The WHO Global Malaria Program maintains a roadmap toward malaria elimination and eradication, updated periodically to reflect the evolving evidence base and the changing landscape of available tools, and the most recent versions of this roadmap acknowledge both the progress that has been made and the very large distance that remains to be traveled before the goal of eradication, the permanent global cessation of malaria transmission, can be seriously discussed as an achievable near-term objective rather than a long-term aspiration. The burden of malaria falls with particular and deeply disproportionate weight on specific populations within endemic societies, and understanding the social distribution of that burden is essential to understanding what malaria actually does to the communities that live with it, as opposed to what it does in the aggregate statistics that epidemiology uses to describe it. Children under 5 years old account for the large majority of malaria deaths in sub-Saharan Africa, and this concentration of mortality in the youngest age group is a consequence of the immunological dynamics of malaria infection. In a higher transmission environment, where older children and adults have acquired some degree of partial immunity through repeated infections, but young children encountering the parasite for the first or second or third time lack the immunological experience to mount an effective defense against severe disease. The death of a young child from malaria is not the dramatic, sudden death of a person in full life. It is often a slower, more ambiguous process, a child who is feverish and unwell, and then more unwell, whose parents and caregivers makes decisions about whether and when and where to seek treatment based on their knowledge and their resources and the accessibility of care, a process that is shaped at every step by the social and economic conditions of the family and the community. Pregnant women are the other population group at particularly elevated risk because malaria in pregnancy causes a specific pathology in which parasites accumulate in the placenta and disrupt the normal development of the pregnancy, leading to increased risks of low birth weight, preterm delivery, maternal anemia, and, in areas of low transmission where pregnant women have not acquired the specific immunity that develops with repeated pregnancy exposure in high transmission settings, increased risk of severe maternal disease and death. The experience of living in a malaria endemic household, of watching children cycle through repeated fevers during the transmission season, of making the calculation of whether this particular fever is serious enough to justify the cost and the distance of a health facility visit, of losing crops during the farming season because the farmers are too ill to work, of paying for treatment out of the household's meager reserves, is an experience that shapes the daily texture of life in ways that no epidemiological summary can fully capture, and that imposes a chronic burden of anxiety, economic strain, and grief that persists year after year in communities where the disease is deeply established. Traditional healers and community health workers in endemic regions have long been the first point of contact for malaria cases in many settings, and their role in the care cascade, in diagnosing, treating, and referring cases appropriately, has been increasingly recognized by formal health systems as an essential component of the response, rather than as a problem to be managed or replaced. A recognition that reflects a broader evolution in thinking about how health systems function in resource-limited settings, and how the knowledge and relationships embedded in communities can be mobilized in service of health. The role of gender in the experience of malaria deserves its own space within this history, because the disease intersects with the social roles and economic vulnerabilities of women in ways that are specific and significant, and that have not always received adequate attention in the research literature or the policy discussions. Women in many malaria endemic societies are the primary caregivers for sick children, and the burden of managing malaria illness in the household, the sleepless nights attending to feverish children, the trips to health facilities, the preparation of treatment, the monitoring of recovery, falls disproportionately on women, adding to the already substantial demands of agricultural work, food preparation, water collection, and childcare that constitute daily life in rural communities. Women farmers in malaria endemic regions bear an agricultural productivity cost from their own illness during transmission seasons, and studies in several African countries have documented the relationship between adult malaria episodes and reduced agricultural labor input, with women's farming activities more severely affected in some settings than men's because of the combination of their own illness burden and the additional burden of caring for sick children. Access to antenatal care, through which intermittent preventive treatment in pregnancy and insecticide-treated nets are delivered to pregnant women, is shaped by gender dynamics that determine whether women have the autonomy and the resources to attend care facilities without their husband's permission, whether the social norms of the community support the use of formal health services during pregnancy, and whether the physical distance to facilities and the out-of-pocket costs of attendance are barriers that women can overcome. The design of malaria control programs has historically been less attentive to these gender dimensions than the evidence would support, and the recognition of gender-sensitive programming as an important component of effective malaria control represents both an evolution in the field and a reminder that the human dimensions of disease, the social structures and power relations and lived experiences that determine how disease affects individuals, are as important to understand as the biological dimensions. It is a gentle reminder, offered here in the quietness of this telling, that behind every case, in every report, behind every statistic, in every surveillance database, there is a person embedded in a family and a community, and a set of social relationships that shape their experience of illness and their capacity to survive it, and that the story of malaria is, at its most fundamental, a story about people, the history of malaria research, the laboratories and field stations and clinical trial sites where scientists have spent their careers working to understand and combat the disease, is populated by figures whose dedication and whose contributions deserve more recognition than they typically receive outside the specialist literature. And it is worth pausing in this chapter of our narrative to acknowledge some of the individuals whose work has shaped the modern understanding of the disease. Adetokunbo Lucas, the Nigerian physician and public health expert who served as director of the WHO's special program for research and training in tropical diseases from 1976 to 1986, was instrumental in building the research capacity of endemic countries and in establishing the principle that the scientists and public health professionals of the malaria endemic world should be central participants in the research agenda, rather than merely the subjects of studies designed and led by researchers from wealthy countries. Pedro Alonso, the Spanish epidemiologist who led the clinical development of the RTS vaccine at the Centro de Investigação em Saúde de Manisa in Mozambique, and later became director of the WHO's Global Malaria Program, spent decades of his career working in sub-Saharan Africa and made fundamental contributions to the evidence base for multiple malaria interventions. Brian Greenwood, the British physician who spent much of his career at the Medical Research Council laboratories in the Gambia and later at the London School of Hygiene and Tropical Medicine, contributed enormously to the understanding of malaria epidemiology and to the development and testing of intermittent preventive treatment strategies. Moses Bokkary, the Sierra Leonean parasitologist who worked on lymphatic filariasis and malaria across multiple African countries and international institutions, represented the generation of African-trained scientists who have increasingly taken leading roles in the global malaria research enterprise. These individuals and the hundreds of researchers and field workers and community health volunteers whose names do not appear in the Nobel Prize, citation, or the journal article byline, constitute the human fabric of the global response to malaria, and their collective work over the past half-century has been the engine of the progress that has saved the millions of lives we mentioned in the previous chapter. It is appropriate, in a documentary told in the long, slow cadences of history, to take a moment to acknowledge not only the disease and its effects, but also the human effort directed against it. The patient, careful, often unglamorous work of science and public health, conducted by people who chose to spend their careers in proximity to suffering because they believed that understanding and action could reduce it. The future of malaria, the direction toward which the long arc of this history is bending, is a subject of serious scientific and public health debate, conducted in the language of modeling and probability and scenario planning, but it is also, at a deeper level, a subject of hope and uncertainty in the specifically human sense, a reflection of the persistent human capacity to imagine better outcomes and to work toward them in the face of very long odds. The tools available to the malaria control effort in the mid-2020s are more numerous and more effective than at any previous point in history, and the combination of insecticide-treated bed nets, indoor residual spraying, artemisinin-based combination therapies, seasonal chemoprevention, preventive treatment in pregnancy, rapid diagnostic tests, and now the first approved malaria vaccines represents an arsenal that, fully deployed, is capable of dramatically reducing malaria transmission and mortality in even high-burden settings. New insecticides with different mechanisms of action are being developed and tested, aiming to address the growing problem of pyrethroid resistance in Anopheles populations that is reducing the effectiveness of existing insecticide-treated nets. New drug candidates are moving through clinical development pipelines, including compounds targeting life cycle stages that current drugs do not effectively address, particularly the liver hypnozoites of Plasmodium vivax that are responsible for relapsing malaria. The field of genetic control of mosquito populations has advanced significantly with gene drive technology, the use of engineered genetic elements that spread through a mosquito population much faster than conventional genetics would allow, reaching the stage of carefully regulated contained trials in Africa, raising the possibility, still distant but now at least conceptually plausible, of using genetic tools to reduce the capacity of Anopheles gambio populations to transmit malaria. Monoclonal antibodies that confer protection against malaria infection for several months following a single injection are in advanced clinical development, offering a potential new approach to prevention that does not require the behavioral compliance challenges associated with daily or weekly prophylactic drugs. The diagnostic landscape is also evolving, with highly sensitive rapid diagnostic tests capable of detecting the very low density infections that older tests missed, allowing treatment to reach infected individuals who were previously invisible to surveillance systems. The artificial intelligence and machine learning tools being applied to malaria. Surveillance data are enabling more accurate prediction of high transmission periods and locations, allowing control programs to target their interventions with greater precision than was possible with traditional surveillance methods. It is a landscape of genuine scientific vitality and genuine programmatic possibility, and the distance between this moment and the moment in 1880, when Laveran first looked at his patient's blood through a microscope and saw something move, is one of the most dramatic distances in the history of human understanding of the natural world. The political economy of malaria, the way that decisions about resource allocation, research priority, and program implementation are shaped by power, interest, and the structures of international relations, is a dimension of the disease's history that cannot be separated from the scientific and medical dimensions. And it is a dimension that has been, throughout the history we have traced together tonight, as important in determining outcomes as any laboratory discovery or field intervention. The history of the global malaria eradication program and its failure demonstrated that even a scientifically well-founded initiative can be undermined by the organizational, financial, and political constraints within which it operates, and that the social contract between the wealthy nations who fund international health initiatives and the poor nations who implement them has always been fragile, subject to the shifting priorities of donor governments and the conditionalities that accompany development assistance. The transition from the era of vertical disease control programs, which focused resources on a single disease in a targeted campaign, to the era of health systems strengthening, which argues that sustainable improvement in health outcomes requires the building of general purpose, health system capacity rather than disease-specific infrastructure, has shaped the funding and programming landscape for malaria in complex ways, with some advocates arguing that malaria-specific investment is justified by the disease's enormous burden and the availability of cost-effective specific interventions, and others arguing that health resources are better invested in building the underlying systems. Trained health workers, supply chains, surveillance infrastructure, community engagement that benefit multiple diseases simultaneously. The COVID-19 pandemic of 2020 and 2021 provided a painful demonstration of the fragility of gains in malaria control, as lockdowns, diversion of health system capacity to COVID response, disruption of supply chains, and reduction of health-seeking behavior combined to increase malaria cases and deaths in multiple African countries in 2020, effectively reversing years of progress in a single year, a setback that was eventually partially recovered as COVID control measures eased and malaria programs were restored. But that left a sobering reminder of how quickly hard-won progress can be reversed when the systems that support it are disrupted. The relationship between malaria control and the broader development agenda, between the reduction of disease burden and the reduction of poverty, between investment in health and investment in education, agriculture, infrastructure, and governance, is one that the most thoughtful voices in global health have long argued must be understood as integrated, rather than sequential, as a set of mutually reinforcing investments, rather than a hierarchy of priorities to be addressed one after another. The story of malaria in literature, art, and culture is a story that runs as a quiet undercurrent through the broader literary and artistic tradition of every society that has lived with the disease, emerging sometimes in direct and explicit depictions of illness and mortality, and sometimes in more diffuse cultural forms, in attitudes toward the natural world, in the aesthetics of particular landscapes, in the social rituals that communities developed around illness and recovery and death. William Shakespeare, writing in England in the late 16th and early 17th centuries, used the ago, the English name for the periodic fevers of malaria, as a reference in several plays, including The Tempest, where Caliban curses Prospero with the disease, and in Henry V, where it appears as a figure for political instability, reflecting the familiarity of the condition to his audience in a way that required no explanation. The poetry of the Italian Renaissance and Baroque periods carries within it, sometimes explicitly and sometimes through the imagery of the Roman Campagna and the Pontine marshes, the atmospheric presence of a landscape that was simultaneously beautiful and deadly, where the golden light of autumn afternoons concealed the invisible agent of the seasonal fevers that would follow. The great colonial literatures of the 19th century, the adventure novels and the travel memoirs, and the official dispatches that described the European encounter with tropical Africa and Asia, are saturated with accounts of fever, with the physical experience of the periodic chills and burning heat that served as the standard background condition of colonial life in malarial regions, and these accounts shaped the European imagination of the tropics as a place of danger and dissolution, a place where the European body was under constant biological siege. Albert Camus, writing in the Algeria where Laveran had first identified the malaria parasite 70 years before, brought to his literature an atmosphere of heat and illness and biological vulnerability that, while not specifically about malaria, carries the emotional residue of a society shaped by endemic disease. The contemporary literature of sub-Saharan Africa, from Chinua Achebe's depictions of colonial-era Nigeria to the work of contemporary writers across the continent, carries the presence of malaria not usually as a dramatic subject, but as a background condition of life, something that characters experience and manage and occasionally die from, in the course of stories that are about other things, in the same way that the disease itself has always been a background condition, rather than a singular dramatic event. The ethical dimensions of malaria's history, the questions about justice, responsibility, and obligation that the disease raises, when viewed through a moral as well as a scientific lens, are questions that become more rather than less pressing as the story moves closer to the present and to the world we currently inhabit. In a world where the scientific knowledge to prevent and treat malaria exists, where the tools to implement effective control have been demonstrated to work, where the cost of preventing a child's death from malaria has been estimated at somewhere between $500 and $1,000 through the most cost-effective interventions, The question of why hundreds of thousands of children continue to die from the disease each year is not simply a technical question, but a moral one. The philosopher Peter Singer's influential 1972 essay Famine, Affluence, and Morality, which argued that the geographical and physical distance between a person in a wealthy country and a dying child in a poor country is morally irrelevant, that we have an obligation to prevent very bad things from happening if we can do so without sacrificing anything of comparable moral importance, is as applicable to malaria mortality as to any other form of preventable death, and the malaria advocacy community has drawn on utilitarian arguments of this kind to make the case for increased donor financing and greater political priority for the disease. The counter-argument, made by some development economists and political scientists, is that the repeated injection of external resources into health programs without the simultaneous building of indigenous fiscal capacity, governance capacity, and political accountability creates dependency rather than sustainability, and that the long-term solution to malaria and other poverty-related diseases lies not in perpetual donor support, but in the economic and institutional development of endemic countries to the point where they can finance and implement their own control programs. Both arguments carry genuine weight, and the tension between them has been one of the persistent fault lines in global health policy debates throughout the 21st century, never fully resolved, always requiring the kind of pragmatic compromise that satisfies neither the philosopher nor the institution builder completely, but that produces the imperfect, partial, gradually improving programs that have in fact been responsible for the progress that has been made. The spiritual and philosophical dimensions of malaria's long presence in human life deserve their own quiet acknowledgement, because the experience of living with a disease that strikes periodically, without warning, without visible cause, in a rhythm that seems almost arbitrary, is an experience that has always generated responses in the religious and philosophical frameworks through which human beings make sense of suffering and mortality. In the ancient world and in many traditional societies today, illness is understood not merely as a biological event, but as a communication, as a message from spiritual forces, or as a consequence of moral or ritual transgression. And the periodic fevers of malaria, with their mysterious regularity, their apparent arbitrariness in choosing their victims, and their resistance to ordinary measures of treatment, generated elaborate ritual responses in virtually every society where the disease was endemic. The propitiation of fever spirits, the wearing of protective amulets, the performance of healing ceremonies, the use of specific prayers and incantations directed at the disease. These practices represented not ignorance, but a rational response to the experience of an illness that seemed to operate according to principles beyond ordinary human understanding. And they provided not only possible therapeutic benefit through the social support and reduced anxiety that ritual can generate, but also a framework within which the suffering of illness could be given meaning and dignity. The transition from this religious and cosmological understanding of malaria to the modern scientific understanding has been, in most societies, a gradual process of addition rather than replacement, with biomedical explanations being incorporated into existing cultural frameworks, rather than simply displacing them, and studies of health-seeking behavior in malaria endemic communities consistently show that families in these communities use both traditional and biomedical resources, sometimes sequentially and sometimes simultaneously, navigating between different systems of knowledge in pragmatic response to the illness that is before them. There is a kind of wisdom in this pragmatism that is worth noting, a refusal to be limited by the boundaries of any single explanatory framework, an openness to whatever helps, that has perhaps served communities in endemic regions better than a more dogmatic adherence to either tradition would have done. The children who will be born in malaria endemic regions in the coming decades will enter a world where the disease remains present, but where the tools to protect and treat them are more effective and more available than at any previous point in human history. And this is a genuine and important fact that deserves to be held alongside the continuing reality of the disease's burden. The generation of children in sub-Saharan Africa who have grown up sleeping under insecticide, treated nets, who receive artemisinin-based therapies when they fall ill, who live in households where their mothers received preventive treatment during pregnancy, have in many areas experienced malaria transmission at lower intensity than any previous generation in recorded history. And while the disease has not disappeared from their lives, its shadow is somewhat shorter than it was for their parents and grandparents. The children who will receive the RTSS or R21 vaccine as part of routine immunization programs will add another layer of protection to those already available, imperfect protection but real, reducing the probability that their encounter with the parasite will progress to the severe disease that kills. The communities that build functioning local health systems, that train and retain community health workers, that maintain surveillance and respond rapidly to outbreaks, that maintain the political commitment to control programs through changes of government and shifts in donor priorities, will continue to accumulate the gains that the tools make possible. And those gains, maintained year after year, will eventually translate into the kind of resilience against the disease that has characterized the regions that have achieved elimination. It is a slow process and it proceeds unevenly, and it is interrupted by crises and setbacks and the recurring complications of poverty and conflict and climate change. But the direction of that process over the long span of history has been consistently toward a smaller domain for malaria and a greater capacity for human beings to protect themselves and their children from a disease that has accompanied them since before they were fully human. The malaria parasite itself, Plasmodium falciparum and its relatives, living in their complicated, ancient, unhurried dance between the mosquito and the human body, continues its existence without any awareness of the enormous human effort directed against it, without any response to its own historical significance, without any sense of the millennia of human suffering it has generated, or the millions of scientific working hours devoted to its study and its defeat. It continues to replicate in the midgut of the Anopheles mosquito, to migrate to the salivary glands, to be injected into the bloodstream of sleeping children in the warm African night, to travel to the liver and divide silently in the hepatocytes, to release merozoites into the blood, to invade red cells and consume their hemoglobin, and divide again, to release more parasites in the periodic bursts that produce the ancient rhythm of fever and chill and sweating that Hippocrates described 400 years ago, doing all of this not because it intends any harm, but simply because it is a living thing, following the imperatives encoded in its chemistry by 4 billion years of evolution. No different in its biological motivation from the Artemisia annua plant that produces artemisinin in its leaves, or the Anopheles mosquito that takes a blood meal to nourish its eggs. or the sleeping child in whose blood the whole ancient drama is now playing out. The parasite has no malice and no mercy, no awareness of the history we have traced together tonight, no knowledge of Laveran's microscope or Ronald Ross's mosquitoes or Tuyu's notebooks or the millions of bed nets hanging over millions of sleeping children across the continent that contains the largest portion of its remaining human hosts. It simply continues, patient and oblivious, doing what it has always done. In the warm darkness, beside the still water, in the long pause before dawn. And yet the history we have traced together across these hours is not a history of futility, not a story about a disease that has always won and always will, not a lullaby of despair, sung over the long defeat of the human body by the invisible world that lives within it. It is, if anything, a story about the extraordinary persistence of human curiosity and human care, about the slow accumulation of understanding across millennia of darkness, and then decades of brilliant, patient science, about the way that knowledge, once achieved, cannot be taken back, about the way that a discovery made in a military hospital in Algeria in 1880, or in a laboratory in Secunderabad in 1897, or in a Beijing research institute in 1972 becomes, eventually, through the long, slow, imperfect but real processes of scientific communication and public health implementation, the material from which lives are saved in villages in Malawi and community health posts in Niger and hospitals in Dhaka and clinics in the Amazon basin. The 600,000 people who will die from malaria this year are a tragedy, and that tragedy is real and should be acknowledged with the full weight it deserves. And the 6 million people who are alive today because of the malaria control gains of the early 21st century are also a fact. And that fact is also real. And the human effort that produced it, the researchers and the program managers and the community health workers and the mothers who hung the nets and the fathers who carried sick children to clinics in the middle of the night. All of that effort belongs in this story, as well as evidence not of victory, but of the ongoing, unfinished, deeply human project of trying to reduce the sum of unnecessary suffering in the world. Here, near the end of our long journey together, through 50,000 years of malaria's history, it is worth resting for a moment in the simple fact of where we are. The disease that has killed, by some estimates, more human beings than any other cause in history, that has shaped the rise and fall of empires, determined the outcomes of military campaigns, driven the geography of slavery and colonialism, powered the development of pharmacology and parasitology and epidemiology and public health, that has been present in the blood of pharaohs and legionnaires and medieval monks and colonial soldiers and African children and Amazon farmers. This disease is still here, still present, still doing its ancient work in the warm, still places of the tropical world. And it is also, for the first time, in the entire span of its relationship with the human species, on the defensive, retreating slowly and unevenly but consistently from the expanding circle of human knowledge and human will and human care. The malaria map of 2026 is smaller than the malaria map of 1950, which was smaller than the malaria map of 1900, which was smaller than the malaria map of 1800. And this long, slow, hard-won contraction is one of the quieter achievements of the human species, less dramatic than the moon landing or the mapping of the human genome, but in some ways more meaningful because it is measured not in technological milestones, but in children who grew up, in harvests that were brought in mothers who survived their pregnancies, in the ordinary, irreplaceable stuff of lives, lived fully rather than cut short. The distance still to travel is long, and the road is not straight, and there will be setbacks and crises, and moments when the progress of decades seems to dissolve in a single bad year. And there will be new challenges, resistance, climate, conflict, pandemic that require adaptation and resilience, and the kind of sustained commitment that is always harder to maintain than it is to initiate. But the direction of that road, looked at across the full span of the history we have traced together, is unmistakably away from the disease and toward a world in which the ancient compact between Plasmodium and the human body is finally, gradually, and with infinite patience, being renegotiated on different terms. And so the long story drifts toward its quiet conclusion, here in the soft space between history and sleep, between the world of ancient parasites and standing water, and the careful scratch of a scientist's pen, and the room where you are lying now, with the sound of your own breathing, slow and even, and the weight of your body settling gently into the surface beneath you. The malaria parasite continues its ancient work, somewhere far from here, in a warm place, full of the sound of insects and the smell of rain on red earth, and the scientists continue their patient work in their laboratories and their field sites, and the community health workers continue their early morning rounds in their villages. And the children sleep beneath their nets, and the world turns slowly in the dark, as it always has, as it always will, carrying the weight of its long history lightly, the way sleep carries the weight of the day, dissolving it gently into something softer and more distant, until it is simply the sound of breathing, and the darkness and the quiet. Let your breath come slowly now. Let the centuries drift past you like water. Let the names and the dates and the long, patient story of the disease and the people who fought it settle into the soft ground of your resting mind, becoming not knowledge but something quieter, not history, but the gentle hum of everything that has already happened, already resolved, already far away. You are here, you are safe. The night is long and soft around you, and the past is very far behind, and there is nothing required of you now except the simple, ancient, deeply human act of letting go and drifting slowly into sleep